All right, awesome. Hello guys, welcome to MTL200 study hall. Somebody is not muted, guys. Can somebody mute themselves, please? Show I'm muted. Okay, perfect. All right, guys. Again, welcome to MTL200 study hall. So in this study hall, we're going to be looking into the theory questions as well as practice questions for your midterm. Okay. So let me answer some of the most popular questions of students from past year and the years before. How to prepare for the student for the midterm. Okay. So the way to prepare for the midterm is only using the textbook. Okay. So this course is fully relying on the textbook, Callister 10th edition. Okay. 10th edition, 8th edition, 9th edition, they're quite similar. But again, Callister textbook, you're going to have a lot of theory questions. Okay. So make sure you read the textbook and do practice problem. I took for this study hall some questions from an older edition of the Callister. Those are pretty good questions, and I saw last year those questions, some of those questions appeared in the midterm. Hopefully that's going to be the case this year. Um, yeah. So, and again, practice problems, you have to do a lot of practice besides knowing the theory, because there are going to be some calculation questions in your midterm. Okay. And again, use my study hall notes. My study hall notes were quite handy last year. Everyone gave a good feedback on that. So basically, my study hall is like a full summary of each single chapter, including the practice questions. So if you're like in a crunch time, a couple of days before your midterm, you don't know what to do, open up my documents, open up my document, go over it, okay, and you will be okay for the midterm. Okay, you're not going to fail it. Okay, but ideally, I would suggest you to read the textbook fully, each single chapter, and do as many practice problems as possible. Okay, so what is going to be on the midterm? There's going to be a lot of theory questions and a load of theory questions. Um, it's going to be like 80% to 20, 80% of theory questions, 20% of calculations. And I would highly encourage you guys to show your work when you're going to be doing calculation questions. Because last year when I was working the midterms, some people uh, like did it correctly, which is like good, they will receive the whole mark. But some people didn't do it correctly. They received like 0 for the midterm. But some people showed the work, didn't have a correct answer. They got 0.5. Okay. So make sure you show some work to get at least some part marks for your questions. Okay. Um, again, a load of theory questions. Make sure you read the textbook, you read my notes, you understand the concepts. If not, email me. I will try to answer emails. I'm gonna actually shoot out my email address right now. Okay, so in case you have any questions, please contact me on my email, or some of you might have my Instagram or my Discord. Okay, so feel free to reach me anytime. I'm gonna be more than glad to answer any questions. That's my email. Okay. Above you can see my website. I'm gonna go over it soon. What is on my website? Okay. So most likely it's going to be multiple choice questions. Yeah, so last year in the midterm, there were a lot of multiple choice questions, pretty much like all of the questions were multiple choice, as far as I remember. So you will have like calculation questions, and your answer is going to be like A, B, C, D, pretty much. You'll have to choose the correct answer. Yeah, so the long answer questions are going to appear in the final exam. Again, midterm is going to be like all just multiple choice questions. And also you're going to be provided the formula sheet on the back of your midterm, okay? But that formula sheet is not going to contain all of the equations. So I would highly suggest you to memorize some of the most important equations. I'm going to go over each equation from all of the chapters that you have covered so far. Okay. Okay, so chapters 2, 3, 4, 5, 9. Okay, so those are from 10th College Tradition. Those are going to be in your midterm. Okay. Again, chapters 2, 3, 4, 5, 9. Okay, so those 5 chapters are going to be covered in your midterm. Additionally, I would suggest you to look over professor's lecture slides. Okay. There is some information that was pretty much used for the midterm last year, remember? So make sure you just look over those, okay, over those slides. Take some notes. learn some concepts from there as well. Those are the same as from the textbook. It's just like whatever professor expects you to know, it's on the slides also. So like make sure you go over it and you understand that. And again, if you cannot answer a question on a midterm, which is quite possible, okay, you don't know the answer to this question, that's fine. Make an educated guess. Um, it's okay. There are going to be like complicated questions in the midterm. You might not know the answer. It's okay. Just make a guess. Okay, that's fine. Like don't just skip a question and forget about it. Okay, so this study hall is going to be a good summary of the important definitions from the textbook. Again, Callister 10th edition. That you must know before you go to your midterm. Okay. I'm going to be also showing you some problem solving questions. I'm going to also solve those questions. We're not going to be able to solve all of the questions that I have in this study hall. So I'm going to be posting my solutions to this document and the document as well, which I already posted in my Dropbox. I'm going to go over it right now. Um, yeah. Blah, 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 blah. Yeah, I'm gonna like basically guys show you some hints, good sources for knowing the information. I made a lot of good summaries for you, some good like table summaries, so you kind of visualize, understand, and you can like recover your from your memory during the midterm. Okay. And yeah, make sure you read every single assigned paragraph from the textbook before you go to your midterm on Wednesday. That was from last year. I didn't fix it. I'm not sure when it's going to be your midterm. Can somebody shoot a date of your midterm? I'm kind of curious because I know it's going to be next week for MTL 200.
On Tuesday.
It's
Quarter
on Tuesday. Okay, it's on Tuesday. Okay, perfect. Yeah, Tuesday 2 to 4 p.m. Okay. And how long is going to be your midterm? 1 hour or 2 hours?
I believe two. I'm not sure.
2 hours. Okay, not bad. Last year there were like 60 questions for the midterm. Yeah, 50 to 70. You're gonna have like 60 or something questions for your midterm. Um, 2 hours is like very reasonable. So shouldn't be a problem in terms of time. Um, yeah, hopefully it's gonna work well. Okay, so let me discuss 1.5 hours, I think is what Prof. Ravi said. 1.5. Yeah, and again, like 1.5 is also like okay for 60 questions. Okay, should be good. Okay. All right, let's
Wait,
discuss the
wait,
structure of the study hall. Sorry, question?
I got a question. Did you say the exam was 80% theory and 20% calculations?
About that, okay. It changes from year to year, but last year, remember, and for my year, it was like a lot of theory and not many calculations. It was like about 80 to 20. Yeah, a lot of theory. Like you're gonna like see a lot of multiple choice questions just based on the concepts, okay, and definitions. Okay. And I'm gonna be like talking about all of this in my study hall and what you have to specifically know for the midterm. Um, yeah. Any other questions? No? I guess I will go over the structure of the study hall now. So I'm gonna summarize and go over the main concepts of each chapter. I'm gonna give you some examples, main problems to solve. And in this study hall, I'm gonna go over 60 questions. Sounds crazy. Eh, like it's not that crazy, but it's gonna be like a little bit of a troublemaking, yeah. But it's gonna be fine as long as you basically watch my study hall, go over the notes in my study hall. You're gonna be fine, and also read the textbook. Okay, you're gonna be fine for the midterm. Um, in this study hall, I'm gonna cover only chapters 3, 4, 5, 9. I'm not gonna go over chapter 2. We don't have time for it. Chapter 2 is like a high school chemistry, so you can do it on your own, guys. I don't remember for the midterm there are going to be some chapter 2 questions. There might be this year. I don't know. Just make sure you just read the textbook, okay? That should be okay. Um, yeah, again, not going to cover chapter 2 in the study hall. Make sure you read the textbook, okay? Some questions might be asked and answered during the study hall, blah, blah, blah. Yeah, feel free to ask any questions during the study hall. Okay, raise your hand or just unmute yourself, message me in the chat. I'm gonna do my best to answer all the questions. Um, yeah, I kind of expect you guys to know some stuff before you come to this tutorial, but it's fine if you don't. We're gonna learn all this stuff now. So yeah, this document which shall serve you as a good start for preparing for your midterm as well. And I would highly suggest you before your midterm on Tuesday, so like some night on Monday, okay, just like open this document, like at 11 p.m. guys, open this document, go over everything, okay? Just like, take a look, go to sleep in the morning, open this document again, go over it and go to your midterm. Okay, so that will definitely help you. Okay, I have a question in the. Hi, sorry, I arrived a little late. Will this be recorded? Yes, that is currently recorded. I'm gonna post this recording. Yeah, and by the way, so I'm gonna be posting the solutions and the document in my Dropbox, and the recording of the study hall is gonna be posted in my YouTube channel. And all of this you will be able to find on my website. Okay, let me send you again my website. https .com. Okay, so here you'll be able to find my again Dropbox, and I will post also my YouTube link to this study hall. Okay, let me quickly show you. So that's my website. If you go here, okay, so here I have the Dropbox link, and this is the Zoom link to the study hall. So if your friends that know the link for the study hall, maybe you can shoot them, a message right now. Here's the link. So yeah, instead of this link, I'm gonna put a YouTube link to my study hall recording, so it should be fine. Yeah, if you click on Dropbox, you should be able to see now the nodes that I'm gonna be currently going over. Okay, perfect. I'm gonna post solutions here as well by the after the study hall. Okay, I guess we're gonna jump into the content of the study hall now. Anyone has any questions before we start? Okay, I assume it's a no. All right, let's start from chapter 3. So chapter 3 covers the structure of crystalline solids. So quick background about this chapter. Every metal on Earth consists of the crystalline structure. So basically, in engineering, we're talking about models always. We want to model some concepts. We want to model the reality in order to be able to apply some equations. Okay. So in this field of engineering called material science, we model metal as a crystalline structure. So what is this? You know that every metal, every object consists of atoms, right? And we approximate an atom as a sphere, okay? So inside an atom, there are billions, trillions of atoms. Inside a metal, there are like billions, trillions of atoms, okay? And if you were to take a look under a microscope, you would see some pattern that occurs there, okay? In three-dimensional, like space, this pattern, we call this pattern a crystalline structure. It's basically a periodic arrangement of atoms. Okay, so they basically repeat each other and they form some structure. Different atoms, they have different structures. There are also, like basically dislocations and other stuff, which we're going to cover in next chapter. So in this chapter, the crystalline structure is perfect. And we're talking about a perfect arrangement of atoms that are located in your metal, okay? So a crystalline metal is one in which the atoms are situated in repeating or periodic array over large atomic distances, okay? So it's basically like atom, okay? So and we're gonna cover the unit cell right now, but basically those atoms, they form again a structure and they repeat each other along basically the block of the metal, okay? Very much. So some of the properties of crystalline solids depend on crystal structure of the material. So the arrangement of atoms matters a lot. Okay, it matters a lot. It will define your density and a lot of physical properties like melting point, freezing point, a lot of physical properties. Okay, so yeah. So lattice. Let's talk about the lattice. Lattice means a three-dimensional area of points coinciding with atom positions or sphere centers. Okay. So lattice directly relates to a unit cell. So unit cell is the smallest repeat unit of a lattice. So basically, lattice is this. So inside your block of metal, you will have those spherical atoms that are creating this unit cell. This unit cell, it's like a block. This block is going to be repeating itself like billions times, okay? And if we assume a perfect model, there are no imperfections in the model, then this unit cell basically propagates throughout the body of your metal, okay? And this allows us to approximate the structure and the physical properties of metal by observing only one unit cell, okay? So inside the unit cell, you will have different arrangement of atoms, okay? And the arrangement of atoms inside the unit cell defines your metallic crystal structure. In this course, we're going to be covering only 4 crystal structures. Beyond this course, there are like a lot of crystal structures. It kind of gets crazy there. But yeah, in this course, 4 crystal structures that you must know. And this is going to be your midterm questions, okay? Because and soon I'm going to be talking about this table. So you must know that you have face center cubic. Okay, this is face center cubic, body center cubic, hexagonal closed packed basically structure, and the simple cubic structure. Somebody's not muted. Okay, perfect. Again, 4 crystal structures: FCC, BCC, HCP, and simple cubic. Okay, this table is insanely important, guys. Okay, you must memorize this table and the numbers inside this table. You will have at least 2 to 3 questions in your midterm that are related to this table. I created this table. It was a really huge help for last year people who basically haven't had a midterm. Let's go over this table. You must memorize it, okay, and all the numbers inside. So we have 4 structures: FCC, BCC, HCP, simple cubic. You must also remember for your midterm the elements that correspond to each crystal structure. Okay, so as you can see, for each crystal structure, there is a different arrangement of atoms. So inside the face intercubic, you can see that there are like 8 of the sphere of an atom that are located in corners, and you have a semisphere, so basically half of the atom. Okay, they're basically located from each side of a 3-dimensional unit cell. So this is a unit cell, okay, guys? So this is a unit cell. So all of this is a unit cell, and we're going to be observing and define the properties inside the unit cell only, assuming that our model, okay, is perfect. So the metal block that you're holding in your hand, we're assuming that it has a perfect crystalline structure, no imperfections, okay, so that we can emphasize our, calculations only in one unit cell. Okay, so this is face center cubic. Body center cubic is a little bit different arrangement of atoms. So what happens is you have one single big atom inside your unit cell, and you have 8, like 8s of your sphere, okay, located in each corner of your unit cell. You have also HCP crystal structure. This structure is quite complicated, okay, and basically this is how it looks like. Yeah, it's quite complicated again. And simple cubic is quite simple, pretty much. So you just have 8 of 8s of your spheres of your atoms. Okay, there's nothing inside. Okay, so it's quite inefficient. We're going to be talking about it. But yeah, that's how it looks. And it touches basically each 8th of a sphere in the corner, in the center of each the unit cell lengths. Okay, let's talk about the elements. So each structure corresponds to element, of course, right? So for this midterm, there's going to be at least one question which is going to ask you which element corresponds, let's say aluminum. This element corresponds to which crystal structure? There's going to be A, B, C, D. You'll have FCC, BCC, HCP, and simple cubic. Okay, and you will have to decide which one is going to correspond to which structure. So you must memorize that copper, aluminum, silver, and arum, they correspond to FCC, okay, the FCC structure. And these elements correspond to its respective crystal structures, okay? Polonium is going to be simple cubic. All of these structures correspond to HCP. Magnesium, okay, please memorize magnesium is HCP, okay? Probably one of the most important is to remember is copper, aluminum, silver. It corresponds to FCC structure. Magnesium, zinc, titanium, HCP. Iron corresponds to BCC, and polonium to simple cubic. That's going to be like most likely a question in the midterm. So make sure you remember this table and remember the elements which correspond to its respective crystal structures. So coordination number, also memorize those numbers, please. 12, 8, 12, and 6. Basically, what is a coordination number? It's how many times, how many atoms, rather, the unit cell touches the other atoms outside of the unit cell, okay? So FCC touches 12 atoms outside of the unit cell. BCC 8, HCP 12, and simple cubic 6. Okay. For those of you who have done your first experiment in your MTL200 labs, you should have covered this stuff. Okay. But again, quick summary of that. Okay, number of atoms. The next row is number of atoms. So number 4 corresponds to the amount of atoms that the unit cell consists of in FCC crystal structure. So let me quickly prove with you why it's number 4. You can basically observe it. You have hemisphere 1 on the other side here, here, and here. So it's going to be basically number of atoms is equal to 0.5 hemisphere, basically. We multiply by amount of times that appears in the unit cell, which is number 4. Okay, and then we have 1, 2, 3, 4, 5, 6 on the other end. We cannot see it. 7, 8 of 1/8. Okay. Wait, give me a sec, guys. That should be number 4 of atoms. So what's wrong here? 1, 2, 3, 4. So 1/8. Okay, times 8. So that's gonna give us 3. Something is wrong. So we have again 1, 2, 1, 2, 3. Oh, we have basically 6 here. Oh yeah, perfect. Makes sense. Sorry, guys. So we have 1, 2, 3, 4, 5, 6 hemispheres inside the unit cell, and we have 8 of the spheres. Okay, so that's going to give us 4. So basically, we have 4 full atoms inside a FCC unit cell. For BCC, that's going to be 1 plus 1, 2, 3, 4, 5, 6, 7, 8. 1 plus 8. Sorry, 1 plus 8 times 1/8, which gives us 2. So there are 2 atoms inside the BCC unit cell. For HCP, not going to be doing this calculation, but there are 6 number of atoms for HCP, okay? Simple cubic, there's only 1 full atom. So it's basically 8 times 1/8, which gives us 1, basically 1 atom, okay? So if you forget the number on the midterm, like number of atoms inside the FCC, BCC, or other structures, and if you visually remember how the structure looks like, you can like quickly prove and find out the number of atoms inside the structure. Okay, so this is the method that you should use. Again, you basically calculate the amount of hemispheres or eighths of spheres, and then you multiply by the number of times it occurs in your unit cell. Okay, atomic packing factor. Okay, so what is atomic packing factor? Atomic packing factor, we do have a formula for this, and there are going to be a lot of practice questions which is associated with this equation. We're going to do a couple of practice questions. Okay, so atomic packing factor in simple terms is how efficient your unit cell is. Okay, so atomic packing factor, the higher the number is, the more you occupy the space, the less you have voids. Okay, so in your unit cell, if you take a look, like in between the atoms, you have like a lot of space, okay? This is quite inefficient for the unit cell, but FCC is one of the highest possible efficient, configurations of your unit cell, okay? So it's not like that much of a free space compared to BCC, which is quite a lot here. Okay, it's a lot of free space here. And simple cubic is like one of the least efficient possible crystalline structures, because it has like a lot of void inside in between those eights of spheres, okay? So the right corresponding numbers, 0.74, 0.68, 0.74. So the atomic packing factor for FCC and HCP is the same. And I would highly suggest you to memorize those numbers because you will not have time on your midterm to actually derive in those atomic packing factors. Okay, question, do the HCP and FCC have similar properties? No, they don't. Basically, physical properties are different. And again, physical properties are also based on other criteria. So I could, like, no, they're not similar, definitely. Even though the atomic packing factor is the same, but it just means how efficient your crystal structure is. It doesn't mean the It doesn't mean that those structures are the same, okay? So no, those are definitely like different, they have different properties, okay? So, okay, and so please memorize those numbers, okay? Very important. Again, you will not have time during the midterm deriving those numbers, okay? And lattice parameter, okay? So what is a lattice parameter? Lattice parameter basically defines the length of your unit cell, okay? So if you say this is A, okay, and if you say that the radius of your atom is this is the radius of your atom, okay, and this is like a full diameter, so 2 radiuses. Can you quickly explain how FCC has a coordination number of 12? Yeah, sure. I wish I had a better figure of FCC structure, like in a 3-dimensional plane, not just the unit cell. But basically, coordination number is the amount of times it's touching the other atoms beyond the unit cell. Okay, so just like memorize, it's 12. Okay, and if you were to take a look at the full version, like not just one unit cell, but like many unit cells, like let's say like a larger block of the FCC structure, you would see that basically the whole unit cell is touching 12 atoms that are outside of the unit cell, okay? That corresponds to the other unit cell. So you do have like a unit cell here, a unit cell here on top, a unit cell here, another one, and on the back and in front, okay? So this unit cell is touching like 12 times, 12 atoms, okay, beyond this unit cell, okay? I believe the textbook also like shows it really well, the coordination number. But yeah, that's pretty much it. Like just memorize it's number 12. That should be okay for your midterm. There's gonna be like at least one question about the coordination number. So please, I encourage you guys to remember these numbers. Okay, please. Very important. Okay. All right. So let's jump back into the lattice parameter. So this is R, and this is A. So lattice parameter, the whole purpose of this parameter is to define the length of your unit cell in terms of the radius of your atom inside your crystal structure, okay? So in here, what we have is radius here. So I will quickly prove you that the lattice parameter for FCC is 2R root 2. For the rest, guys, you will be able to prove it yourself, okay? Here is quite simple. Since this is A, and this is R. Okay, let me quickly remove this mess here. So if this is R, this is A, so your A is equal to 2R. So it's quite simple in simple cubic, okay? That's why we have 2R. So the length of the unit cell, you want to represent this in terms of radius of your atom, again. So the length of the unit cell for simple cubic is 2 radiuses of the atoms inside this unit cell, okay? Perfect. For this guy, let's determine now the amount of, or the length of the unit cell. Okay, so here you can observe that we are forming the triangle here. Okay, so this triangle is pretty much going to be 4 radiuses, and this is A, and this is A. Okay, this is A, and this is A. So simply by Pythagorean theorem, you have A squared plus A squared is equal to 16R squared. So 2A squared is equal 16R squared. Okay, so, and yeah, so A squared is equal to 8R squared. And then you have A is equal to square root of 8R squared, which is equal to 2 root 2R. Okay, which is the same as this, 2R root 2. Okay, so what do we have to prove, derive lattice parameters, or is memorizing them fine? Memorizing them is perfectly correct, and you have to memorize it. I'm just showing you guys in case you forget, because I do understand we do have a lot of midterms, and like, it's quite heavy. The semester is quite heavy. So in case you forget it, I'm showing you the strategy on how to derive it, okay? but it shouldn't be too hard to memorize it. But on the whole scale, you will have to memorize a lot of things for your midterm, okay? So just in case you forget it, this is the approach on how to derive this, okay? Anyone has any questions on this? I can go over it if somebody didn't understand it or anything else. Let me know in the chat, please, okay? Or just unmute yourself. BCC 4R over square root of 3. This is the lattice parameter. And yeah, guys, you can prove it on your own, okay? For the HCP, just like memorize it, okay? 24 root 2 R cubic, and simple cubic is just 2R, okay? Let's mention the density formula, because we will have a lot of practice questions, which are going to be like, hey, calculate the density of, you know, this crystal structure or blah, 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 blah. Okay, so the equation for the density is this equation. Okay, so that's the number of atoms inside of your unit cell. It's a number of atoms inside unit cell. A is atomic weight, and atomic weight you can always, it's going to be either given to you, or if you don't see it in your question, find it in the periodic table. Okay, periodic table should give you atomic weight. On your midterm, you're going to be given atomic weight. Don't worry, that should be okay. So VC is the total volume of the unit cell. Okay, so it's not what you occupy with your atoms, it's just the total volume of the unit cell. And VC is always going to be A cubic. Okay, and you always want to relate your length of your unit cell to the radius of your atom. So that's why we defined lattice parameter. It is very important, okay? So it's going to save you a lot of time in your midterm if you do remember your lattice parameters. Because when you're going to be calculating your densities, you'll have to use your total unit cell volume. So you will have to use radiuses of your atoms.
Sure.
Basically, in terms of lattice parameter. Yep, question?
So for the HCP, is that C value? Is that technically like the A value for the rest?
Oh, C value? You're asking about this C value?
Yeah, does that act like the A value?
No, in HCP structure, you have three parameters. You have A and C. C is basically height of your HCP structure, okay? Okay, C is the height of your structure, and the height is going to be 4 square root of 2 or 3R. Okay, I'm not going to be deriving this, but if you're interested, I don't remember if the textbook derives that, but some YouTube videos, you might just watch it, okay? Okay, and on the midterm, I'm going to tell you last year, there were no HCP questions, as far as I remember. You might get some HCP questions on this midterm this year, but it's not going to be something super crazy like, you know, deriving something. You might be given, yeah, you might be given like calculate the density of magnesium or something. And you must remember that magnesium is HCP, right? So you'll have to use just the unit cell volume, okay, which is 24 root 2 R cubed. Okay, so memorize with this value, okay, guys? Yeah, that's pretty much it. HCP is complicated, okay? There's going to be some Miller indices like questions related to HCP. We're going to see if we're going to be able to cover it in the HCP structure, but yeah, it's quite complicated, three-dimensional structure. So just make sure you memorize this unit cell volume, atomic packing factor, number of atoms, coordination number, and the elements that correspond to the structure. Okay, guys. Any other questions about the HCP or anything
I have a
else?
quick question.
Yep, sure, go ahead.
For the unit cell volume for HCP,
Mhm.
since it's already the volume, would you have to cube that one? Because isn't the other one's A cubed?
So that's already given to you. That's already cubed. Yeah.
So you don't need to
I
cube this, right?
no. That's already the
Okay.
volume. I just gave it to you because of the like when I was creating this table, just like you know, a quick summary so that you can memorize things. So just make sure you memorize
Okay.
it. So this
Thank you.
is already cubic or you cubed, sorry. So just memorize it. You will have to cube this. And like I didn't cube it for you guys, like just cube it yourself, like it's fine. Not that complicated, right? Um Okay, question here. Is there going to be a recording posted? Yeah, I'm going to post a recording. Yeah. Yeah, I'm going to post it on my website. I posted my website somewhere on top of this discussion in the chat here. During the break, I'm gonna post it again. Okay, so don't worry about it. Okay. Okay, now important definitions. Okay, so make sure you remember those definitions. Very important. So polymorphism. Basically, in simple terms, what is a polymorphism? Polymorphism is when you have a load of different crystal structures inside your metal. Okay, so you might have like FCC, BCC, HCP inside your metal. Okay, that what is a polymorphism. Please remember this. Might appear in your midterm. Also, allotropy is when you have more than one crystal structure in a chemical element. Just like memorize those definitions. Okay, might be asked in your midterm. Sorry, can you explain what does Na stand for in the density formula? Oh, it's Avogadro's number. Sure. Yeah, sorry, I didn't go over it. On top of my memory, Avogadro's number is 6.022 times 10 to the power of 23, I believe. Can somebody confirm? Because like I don't remember. I think that's the value of Avogadro's number.
Yeah.
Yeah, okay, perfect. Okay, fantastic. That should be it. Yeah, okay. Any other questions before I move on to another page? Any questions about the table? Okay, I assume it's a no. Let's move on now. So let's talk about crystallographic directions now. Okay, we're going to be talking about the Miller indices. Okay. So on your midterm question, you might be asked to basically draw like a line or a plane. Last year in the midterm, there were no questions about that. Okay. On your final, you will have one question like that. Okay. So I would suggest you like go over it, make sure what is what. I'm gonna give you the a structure and approach, okay, on how to basically tackle those problems. Yeah, but like don't expect it for your midterm, but be prepared, okay? For your final exam, like 100% you will get this question, 100%. It's gonna be like plain question for your final exam, 100%. For the midterm, perhaps you might not get it, but it's okay. Just know the approach, okay? So in your square brackets, when you're talking about crystallographic directions, you want to define basically how it looks like, and in order to communicate between material science engineers, basically we defined the crystallographic directions and the rules. Okay, so inside the squared brackets, you always define your crystallographic directions, and inside the brackets, you will always define your crystallographic planes. Okay, please make sure you remember that. Very important. So again, brackets, they correspond to planes. Okay, and your squared brackets, they always correspond to your direction. Very important, okay? So you might be asking the midterm, what is this? It is a family of directions. So basically what a family of directions mean is basically combinations of this number, so 100, and inside your crystal structure, like right, you might have different combinations. So this family of 100 will mean that it might be aligned this way, this way, this way, or that way. So I do have a summary somewhere later of all of the crystallographic families, all of like family of directions and planes that you should remember. So I will show it to you later, but just like understand that this is like a family of directions and this is the just one direction, okay? And the family of directions is basically a combination of possible directions, okay, that are defined by these three numbers, okay, which are called, by the way, Miller indices, okay? So let's talk about the strategy now. So let's say you're asked to find in this question, so 0, 1, 1, right? So let's say you were asked to draw the crystallographic direction. So I will teach you guys how to easily approach it, okay? So you have to start from your origin. The first step is to always pick your origin. Usually when you have all positive numbers, they're all positive, okay? And if you have a negative number, you will always have a bar on top here, okay? So in here, all numbers are positive. So you define always, if all numbers are positive, origin as this point, as a typical origin of your coordinate system, okay? Then you want to factor out the common number, if applicable, inside your crystallographic direction. So in here, you cannot factor anything out because like it's 0, 1, 1, okay? But let's say in this number, you can factor out 2, okay? So if you were to factor it out, you would divide each number by a factor of 2 here. So it would be 0, 1, and 1/2, okay? So that's the second step. So in this example, again, we started from picking the origin, then factoring out all common numbers that we have inside our crystallographic direction, okay? So there are no common number, so it just stays as it is. And then after that, you have 0, 1, 1, so you just have to follow your regular x, y, z coordinate system. So very simple. So this defines your x coordinate, y coordinate, and z coordinate, okay? So since this is your origin, you have x-axis, y-axis, and z-axis, okay? So on your x-axis, you go nowhere, so you just stay at the origin. On your y, you go 1, and 1 is a unit cell, okay? So it's a unit cell length, okay? Basically, each coordinate of your unit cell is 1 here, it's 1 here, 1, 1 coordinate. This is going to be 1, 0. This is well, since this is 3-dimensional, so it's 1, 1, 0. This is 1, 0, 0. This is going to be 0, 0, 1. Okay. So again, x, y, z, you go 0 on the x-axis, 1 on y-axis, and you go 1 on z direction. And then you draw your vector. Okay. Make sure you have your vector, which points to the last point that was defined inside your crystallographic direction. Okay. Any questions about that? Should be quite straightforward. Okay. Make sure for a midterm or for a final exam, you remember the strategy. Okay. You start from picking your origin, you factor out all common numbers, and you just follow regular x, y, z plane. Okay. Any questions on that? No, should be quite simple. Yeah. Okay, let's move on to the second example. So we have 0, 2, 1. So what's the first step, right? We pick the origin. And we pick the origin in this regular, origin location if all numbers are positive. And as we can see, all numbers are positive. We're good. So we pick the origin here. Second step, to factor out all common numbers. So we factor out 2. We have 0, 1, 1/2. Okay, the third step is to understand that we have x, y, z coordinate system. So we will need to move on to respective, distance of x, y, and z, which is defined here. So on x, we go nowhere again, we just stay the origin. On y, we go to 1, so we travel here. And then we go 1/2 on the z-axis, okay? And what is 1/2? 1/2 is the half of the unit of the unity here. It's half of the length here. So you just eyeball it and you draw it like that. Okay. So this will give you 0 to 1 crystallographic direction. Okay. So quite simple. Any questions on that? No. Okay. Let's move on to this example. 2 bar 1, 2. So as I said before, this means negative. Okay. It is negative. Okay. So first step is to pick your origin. And as I said before, we pick the origin always here if all numbers are positive. However, here we have one number as negative. So the trick here is to always stay inside your unit cell. In order to do that, you know that after you factor out everything, you will have 2, 1 bar, 1/2, and 1. Okay. So what that means is you have -1 coordinate. Oh, sorry guys. Give me a sec. Somebody was calling me. We're back. Can you see the screen, guys? Can somebody confirm?
Yep.
Yeah, you're good.
Okay, perfect. Thank you, guys. Awesome. All right. Where did I stop? Oh yeah, here we go. So basically, in terms of your coordinates, you have -1, 1/2, and 1. Okay. So the trick here again is to stay within your unit cell. So in order to do that, you want to move your origin at the point where you have your negative. Okay. So if you were to start from your original origin location, you would move -1 outside of your unit cell, which is okay. But for a lot of students, I noticed that it's really hard to visualize and work outside of the unit cell. Okay. You can construct another unit cell here, like the same unit cell. Okay. And then you can work, which is fine. That's going to be simply, so if you start from here, you will go here, -1, you go 1/2 here, and you go 1/2 up. Okay. No, you will have, yeah, you'll go here and 1/2 up. So you will go like that. That's quite messy, quite hard. Okay. You can do that, which is quite fine. But my trick is to stay within the unit cell always. Okay. And in order to do that is to move your origin here so that when you go -1, you still stay within the unit cell. Okay. So if you have -1, you move your origin here so that when you move -1, you still are within your original unit cell. Okay. And then you go 1/2 here on y and z 1. So you can draw your vector here. Okay. Any questions about that? Any questions about why I moved the origin? Any other questions? No, it should be quite straightforward. Yeah. Okay. I suppose, yeah. Okay, perfect. Let's do one example. 3, 6, bar 9. Okay. The origin moves just if x is negative or also, yeah, so the origin will, we're gonna do this example now. The origin will move according to your number which appears. So it can be -x, and it can be -y, -z. Anything can be negative. Okay, so you want to move your origin with respect to your negative number. Okay, there might be even two negative numbers. Okay, so you have to like, work things around. So this example I will show you how to do with -y. Okay, so I would like to use one of these unit cells. Let me use this unit cell. So I'm gonna erase my annotations here. And okay, 3, 6, bar 9. Okay, what is our first step? First step is to pick your origin. Okay, so here we understand that we have -y number, right? So let's firstly factor it out. Okay, see what is going to be this number after we factor it out, and then we can pick our origin, right? So the highest number that we can factor out is 9. So let's factor out 9. That's going to be 1/3. It's going to be 6/9, which is 2/3 bar and 1. Okay, so we can ignore this number 9. We don't need that. What we care about is the coordinate of our endpoint of the vector. Okay, so it's going to be 1/3, -2/3, and 1. Okay, so right now our y value is negative. Okay, our y value is negative. So our typical origin is right here. Okay, so we want to create a new origin such that when we move -2/3, we're still staying within the unit cell. Okay, so you can pick your origin here. Okay, just simply right here on the edge of the unit cell. So you move -2/3, okay, which is like -0.67. So you move somewhere here. Okay. So that's how you want to define your origin. Okay, so just like offset your origin so that when you go on the negative scale, you're still staying within your unit cell. Yeah, so let's start from, so this origin, right? We go 1/3 in positive x-axis, so it's right here. Then we go in -2/3 here, it's somewhere around here. And then we go in 1 up, so 1 up here. So you always draw your vector from the origin to the endpoint. So that's going to be your vector. Okay. So this corresponds to your 3, -6, 9. Okay. Any questions on that? Could you show it again? Yeah, sure. So 3, 6, bar 9, you factor out here 9. That's basically the highest number here. You factor it out. You divide 3 by 9, 6 by 9, and 9 by 9. Okay, you will get 1/3. You will get 6/9, which is 2/3, and you will get 9/9, which is 1. Keep in mind this number is negative, so you ignore this number and you write down this. So this is your like coordinate x, y, and z. Now you need to define your origin point. Your typical origin is here. Okay, your typical origin is here. Then you move, so you want to move your origin so that you still want to stay within your original unit cell, which is this unit cell. Because if you define your origin here, then you go here, you're going to be outside of your unit cell. Okay, you don't want to do that. It's going to be quite confusing. So define your origin right here. Okay, basically on the 1, 0 or 0, 1, 0 location. 0, 1, 0 location, so that when you move -2/3, you're still staying within your unit cell, okay? And then just follow the coordinate system. Your first is x, so it's 1/3 positive, then -2/3. So you just go here. So that's just -2/3, so you go in the other direction. Then you go up by 1, right? Up by 1, and you draw your vector, which is always going from your origin to the end point, okay? And your end point is here. Since this is 1/3, -2/3, and 1. Okay, we do have a couple of questions here. Oh, just one question. If there are 2 negatives, then which origin do we take? If you have 2 negatives, then basically, okay, good question. Let's find an example. Let's say we have 1 bar, 1 bar. If you have 2 negatives, there might be a chance you might go outside of the unit cell. I don't know. Let's see now. So if you have 1 negative, and 1 negative, right? So basically 1 negative, 1 negative, 1. So your y is negative, your z is negative. So if you were to have origin here, well, you can still stay within your unit cell. Okay. So you move your origin point here, so that when you move x here, then you move y down. Okay, and then you go, oh, sorry, y down is going to be this way, right? And then z down is here. So that's going to be your vector. So you can still stay within your unit cell, even if you have 2 negative numbers. And let's say you have 3 negative numbers. You have -x, -y, -z. So you can define your origin like here. That's going to be your new origin. So you go -1, -1, -1. So your vector is going to be like that. So quite simple, okay? Should be understandable. Any other questions about the directional crystallographic directions, guys? No? Okay, should be good. Okay, let's jump into crystallographic planes now. So plane definition in a crystal structure, as I said before, you define your plane by these brackets, just regular brackets, okay? And the family of planes is going to be defined in the curly brackets, okay? Similar to crystallographic directions, you have this sign. Your family of planes is going to be defined inside your curly brackets. Okay. Right, so let's do a couple of example questions on that, and we're going to be jumping into other definitions and things inside this chapter. So, okay, planes. I'm going to teach you guys a strategy how to tackle down those problems easily. Okay, so let's say you want to find, you were given a plane. Okay, you were given a plane and you want to find the how your basically plane can be defined using the Miller indices. Okay, there's going to be some number x, not x, right? Some number a, b, c. Okay, so you want to define this plane in terms of your Miller indices. Okay, so the first step is to take basically the coordinates of each point where it intersects the XYZ coordinate system here. So here we can observe that this triangle A will intersect the X at 1/3. Okay, so you define your origin here. Okay, so just define your origin here because it's quite simple. You go this way, and you go this way. Okay, so 1/3 is positive. You go here. You go to the right, positive 1/2, and you go down negative 1/2. Okay. Then the next step is going to be to take the reciprocal. Okay. So when you take the reciprocal of 1/3, right, you will just get 3 pretty much, right? So you will get 3, 2, and -2. Okay. And since this is negative, you will have to put it in terms of the Miller indices, right? You will have to put a bar on top for negative number. So 3, 2, 2 bar. So this, if you were to given this, you can go backwards and create this plane, and we're going to practice that. So this plane can be defined as 3, 2, 2 bar. Okay. Any questions on that? So you take the coordinate, you do the reciprocal, and you will get that number pretty much. Okay. Any other questions? No. Okay, cool. Let's now observe this plane. So this plane is quite unique. As you can see, it doesn't touch the y-axis. Okay. So let's first take the coordinates of each axis where this plane intersects. Okay. So we can pick our origin as here. Actually, we don't need that. We can pick the origin here. Let's say, okay, let's pick the origin here. So on x-axis, right, it will go to negative 1/2. Okay, basically this is 1/2, right? So you go not to this direction because this direction is positive, right? Defined as positive. So you want to go to this direction. Is it 0 on y? So I'm gonna talk about that. It's not going to be 0 on y. In terms of Miller indices, it's going to be 0, but it's actually infinity, right? Because it doesn't touch the y-axis, right? So let me talk about it. So on x-axis, your plane B will intersect at 1/2, and it goes to the negative direction. So you define this as negative 1/2. Now y. So what happens on your y-axis? As you can see, this plane is parallel to your y-axis here. So it doesn't touch your y-axis. When you see that something is parallel to the axis, you want to put infinity here. Okay, put infinity. It never touches. Think about it like that. The plane never touches the y-axis. It's at the point of infinity. Okay, so never touches. Okay, and your z-axis is going to be positive 1/2. Next step is to take the reciprocal. Okay, so reciprocal of negative 1/2 is -2. Reciprocal of infinity is 0. Okay, and the reciprocal of 1/2 is 2. And since you have negative number and you have a common factor of 2 here, you can factor out 2 and use Miller indices notation to put a bar on top. Okay, you can ignore 2. So your final look is 1 bar, 0, 1. Okay. So if you were to define this plane in terms of Miller indices, that plane would be 1 bar, 0, 1. Can you explain why it is -2? Right, so on the x-axis, right? So let's say this is your origin. Okay, when you go here, right, you see that this plane touches your x-axis in this location. Sorry guys, again. Okay, here we go, I'm back. So you have 1/2 here, and it goes to the negative direction. So since this is 1/2 and it's a negative direction, in your coordinate system, this plane exists at -1/2. Okay, so when you do the reciprocal, you will get -2, and then you factor out 2, you will get -1. Okay, does it answer your question? Could we put the origin at 0, 0, 0? You could put the origin. Jesus Christ, sorry guys. Let me send a message to whoever's calling me. Give me a sec. The purple sheet. Sorry guys, give me a sec. Okay, cool. So 1 bar 0, 2. Sorry, 1 bar 0, 1. Okay, that should be it. Is it possible for you to run through the planar explanation one more time? I was unable to hear it. I had to answer something wrong. Okay, sure. I'll do it quickly, okay? So let's say this is your plane, okay? You define your origin here. And the first step is to take the coordinate system of basically the locations at which your plane intersects your x, y, z coordinate system. So that's going to be 1/2. You define your origin here. That's a -1/2 location, okay? Then you go to 0. Sorry, your y coordinate system. So since your plane does not touch your y coordinate system, this is going to be like infinity, like an asymptote. Okay, so you define this as infinity. And then your z coordinate system is 1/2. Okay, the next step is to take the reciprocal, so -1/2 of each single number here. So -1/2, the reciprocal of infinity is 0, and reciprocal of 1/2 is 2. Okay, and then you factor out your 2. That's -1, 0, 1. Okay, and then you use your Miller indices notation, and you drop this 2 out. You will get 1 bar, 0, 1. Okay, so that's how you define your plane in terms of Miller indices. Okay, so let's do practice problem now. We'll have to reverse it now. We're going to be given the Miller indices, so we'll have to find a plane. If you were to take another point as the origin, we'll get the same answer. No, the answer would be different. Because yeah, factor out -2. Wouldn't you get a different answer if you factor? No, you never factor out negatives. Okay, please never factor out negatives. It is one of the rules. Never factor out negatives. Okay. Okay, never factor out negatives. So just factor out the highest number or the common number that you have. Okay, but you should never factor out negatives because this will be not correct. You will not get a correct answer. Okay, so never factor out negatives. Okay. Yeah, but if you were to answer the previous question, if you were to take the origin here, your answer would be different. But basically, it's not incorrect. Okay, you can still define your origin here. Okay, and then you can go and take a look at where it intersects. Okay, but I would suggest you to take your origin at the simplest possible location, which is going to be quite obvious because it's right here. So if you go here, you can see that your plane touches here, your plane touches here. Okay, so that's quite an obvious location. So I would expect you to just identify this obvious origin. Okay. let me show you another set of examples. So we have 2 bar, 1, 2, and 0, 1, 0. Okay, we have 2 bar, 1, 2. Okay, so let's work backwards now. Okay, so we want to decide what is our origin. Okay, and since we have a negative number, okay, we do understand that we'll have to move the origin from our regular location, right? So let's take this down right here. So we have 2 bar, 1, 2. So that's going to be -2, 1, and 2. Let's take the reciprocal now. So we'll have -1/2, 1, and 1/2. Okay, so here basically those are your coordinates. Okay, so you define your origin as in the example of your crystallographic directions. You want to move your origin so that you can satisfy the condition of having your plane inside your inside your unit cell. So -1/2 means that we'll put our origin here, and we're going to go -1/2 here. Okay. Then the next interception point is going to be 1. So now it's not going to be like a vector, right? We're not going to be going here, here, and somewhere here. Now we're using our origin as the main reference. So -1/2, we go here. That's going to be our -1/2. Now 1 away from the origin, we go here. Okay, and then we have 1/2 positive when we go here. Okay, so using those 3 points, sorry, you can construct your plane now. Just like that, and like that. Okay, and make sure you do that. So that's your plane, guys. And this plane, you can define as 2 bar, 1, 2. Okay. Let's do another example now. 0, 1, 0. Okay, so let's take it down. 0, 1, 0. Let's take the reciprocal of it. We have infinity, we have 1, and we have infinity. Okay. So now, right? So we have x, y, and z. Nothing is negative. Sorry, could you explain why x is the origin? So the x is the origin is because we have the number here as negative. Okay. So if we were actually to put our origin here, we would go beyond the unit cell. It would be quite confusing, but still doable. Like it's not that hard. You can still define your origin if you feel it's like complicated for you as here. The reason I want to move the origin is so that you can still stay within your unit cell. Okay. So in order to do that, you want to move your origin so that you're staying within the unit cell. Okay. So since this is -1/2, you want to move your origin away to this point so that when you go -1/2, you're still within this unit cell. Okay. Hopefully that does answer your question. Okay, perfect. So we have infinity, 1, and infinity. So x, y, z. So what it means that if we define our origin here, okay, oh shit, let me go back here. Whatever. Here we go. So if I define my origin here, you have x is equal to infinity. So it's never touching the infinity. Sorry, it's never touching the x-axis at infinity, basically. You have y-axis, so you go here at 1, okay? And then it basically never touches the z-axis, okay? So 0, 1, 0 is simply this plane. Okay, so this is this plane, this rectangle, okay? And this is like a very simple example of this plane, okay? It never touches your z, never touches your x. It only exists as basically here and here everywhere, okay? So it's just your 1, 0, 1, 0 plane. As a quick example, you can also like define your 1, 0, 0 plane. So it means that this is going to be this plane, 1, 0, 0, 0. Your 0, 1, 0 plane is going to be 0, 1. Oh, well, we just did 0, 1, 0, and you have 0, 0, 1. So 0, 0, 1 is going to be only that plane. Okay. Those are like typical planes that you kind of can easily identify without doing the step-by-step, right? Just taking reciprocal and blah, 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 blah. Okay. Any questions on that? Should be quite straightforward. Okay. Just memorize the strategy. Does a plane 0, 0, 0 exist? Well, 0, 0, 0 is just your origin point. Okay. It's just a point. It's not a plane. Okay. All right, let's jump into the definition of linear and planar densities. So linear density, okay, is basically how packed. So you have this vector that we defined before, right? This is like a line, a vector. So you want to identify how many atoms are intersected by this vector, okay? So how packed this line is pretty much. So how many atoms are here, okay? So here's an equation for the length of the direction vector. Yeah, so you have the number of atoms centered on the direction vector divided by the length of the direction vector, okay? So how dense your crystallographic direction is, basically you want to represent this in terms of how many atoms are touching this line per the length of the vector, okay? And obviously you have a planar density. So you want to identify the number of atoms that are located on this plane, right? And then you want to divide this per area of the plane, okay? So you want to identify the planar, the density, how many atoms are located on this plane, pretty much, okay? So we're gonna like do some examples at the end of the chapter, okay? This is the table I was talking about, okay? So oh, well, that's a little bit different table. So this is like the closest packed planes, okay? So this relates to this, okay? Relates to this. Very important, guys. You must memorize this table. There's going to be at least one question in the midterm where it's going to be asking you, what is the closest packed plane for BCC structure? Okay, and you're going to be given like A, B, C, D, a whole bunch of like stuff like random 0, 0, 1, blah, 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 blah. And one answer is going to be 1, 1, 0. There's going to be only one correct answer. So please memorize this table. So for FCC, your closed packed plane is 1, 1, 1, 1, 1, 0 for BCC. This is the closed packed plane for HCP, and for simple cubic, that is the closed packed plane. The same story happens for direction of the closest packed directions, 1, 1, 0, 1, 1, 1. This is the closest packed direction, and for simple cubic is that, okay? So in the practice questions, we're going to be deriving one closed pack plane or direction. I think it'll be a plane. So yeah, I'm going to give you like one example, but I will suggest you please memorize this table. Very important. Okay. Please memorize this table. Okay. So let's jump into the closed pack crystal structures now. So we have HCP. Closed pack crystal structure, right? So in the closed pack crystal structure, you always have a stacking sequence. Okay. So that stacking sequence, you also have to memorize for two crystal structures. Might be asked on your midterm. So for HCP, that stacking sequence is AB, AB, AB. Okay, that's pretty much this example. So what it shows you that you have like one layer of atoms, then another layer of atoms. Those layers are not similar. They're a little bit offset, basically like offset. Okay, so for that, for HCP, you're repeating like cycle is going to be AB, AB, AB. So inside magnesium, you will have like one layer like that, another layer like that, like that, like that, like that. And we basically identify this as a stacking sequence. And for HCP crystal structure, it's AB, AB, AB. And for face center cubic, you will have three different layers, basically a different stacking sequence. That's going to be ABC, ABC, ABC. Okay, just memorize it. Might be asking your midterm. Okay, that's called the stacking sequence. Okay, let's talk about a couple of definitions. Single structure, polycrystalline, grain boundary, non-crystalline, and isotropy and isotropy. You have to memorize all of those, okay? The most common definitions that appear in the midterm are anisotropy and isotropy. Please memorize it. Anisotropy is basically directionality in properties, and isotropic is basically no directionality in properties. Just memorize it, okay? Grain boundary is atomic mismatch. We're going to be talking about it a little bit later. Single crystal is the periodic arrangement of atoms, no grain boundaries, okay? Polycrystalline You have several crystals having different crystal orientations. Okay. So guys, give me a second. All right, back. Okay, non-crystalline is amorphous, no system arrangement of atoms. So basically, non-crystalline is like a liquid or a gas. Okay. Here in this chapter, we're talking about solids only, like metal or something, right? They have a defined crystal structure. And as a non-crystalline means it's amorphous, so it's a liquid or a gas. It doesn't have a defined crystal structure. Okay. All right. Let's talk about the Bragg's law now. So some of you should have had your experiment number 3, as far as I remember, or experiment number 2. It's basically called X-ray diffraction. Okay. In this experiment, you basically define an element based on the high intensity arcs, right? That were taken during your X-ray diffraction experiment. Okay. And using the Bragg's law equation, you can define basically the wavelengths of your element, okay? And that wavelength is tabulated for each different element. And based on the wavelengths, you can define what is your element, okay? So the Bragg's law can be defined by using this equation, okay? So these equations, basically, this is the main equation of the Bragg's law. And DHKL is pretty much just I believe it's called the distance inside your a unit cell is based on the Miller indices. So you will be given like 1, 1, 1, and you can define your DHKL based on the unit cell parameter. Okay, an edge length, yeah, A is an edge length, yeah, A is an edge length, and A is basically, let's go back to our glorious table here. It's lattice parameter, okay, and lattice parameter is defined by your R, the radius of your atom, okay. So yeah. So A is your lattice parameter, and your HKL are your Miller indices. So that basically relates back to our work that we've done here, basically Miller indices, okay? So you have to memorize this table, okay? This table is very important. I took it from the textbook, this table, but in the midterm, you will have questions about the Bragg's law for sure. And you will have to remember basically how you'll be able to find your DHKL is based on the crystal structure. So in the question, you'll be like asked, find like the wavelengths, let's say, of the element, given that this is a FCC or BCC crystal structure. So based on the given crystal structure, you must remember that if it is a BCC, your Miller indices, if the sum of the Miller indices is even, which corresponds to a BCC crystal structure, this is going to be like the possible variations of your Miller indices, okay, reflection indices, okay. So we're going to do one example. I'm going to show how this works. Okay, so for FCC, if your HK and L are either odd or even, this is going to be another set of Miller indices that you must remember, okay? And for simple cubic, it's all, but you're going to be on the midterm ask either BCC or FCC, but we're going to do one example of that, okay? So what does D represent? I honestly don't remember exactly what that represents. If somebody had a lab from an experiment for the Bragg's law, please shoot it in the chat. Yeah, last time I was doing the study hall, I honestly forgot what the DHKL means. It's like a distance parameter. Yeah.
I think the DHKL is the distance between the two planes.
Two planes. Yeah, perhaps. Yeah. So apparently, like the distance between, let's say, this top plane and this plane is going to be like that. Take a look at the textbook, please. I forgot what does D represent. Okay. Oh, N basically is a reflection parameter. You always define this as 1. Okay. In your question, you might be asked explicitly to define this as a 2 or any other number. But if it's not given, always define your N as 1. Okay. So N is 1. For DHKL, please refer to your textbook to just remember what does this represent. Okay. But no matter what, we're gonna do one example question, and we're gonna like solve with the Bragg's law, okay? Using the Bragg's law equation. All right, let's do a couple of questions, example questions, okay? So I'm gonna leave this, guys, for you to do example, because that's gonna take a lot of time, and it's been like already an hour for the study hall. It's only one chapter that we covered. So, right, so please do it on your own. I'm gonna post answers to my to the study hall, so you're gonna be able to refer. Please practice. I explained the strategy, should be quite simple, okay? So let's do the first example. Okay, so we want to calculate the radius of vanadium atom, given that vanadium has a BCC crystal structure, a density of 5.96 grams per centimeter cubic, and atomic weight of 50.9 grams per mole. Okay, so let's write down what is given. Okay, what is given? So we're given that we have vanadium atom. We have vanadium atom. We have a BCC crystal structure. We have a density of 5.96 grams per centimeter cubic. Okay, and we have an atomic weight of 50.9 grams per mole. Okay, and what we're looking for is the radius of vanadium atom. Okay, so the way to approach this problem is to firstly understand that you have a defined crystal structure. You have a BCC crystal structure, right? And also you are given a density, right? So remember that the density has a certain equation that we can use. So let's scroll up. So this is the density equation. So rho is equal, let's rewrite this. Rho is equal to NA divided by VC NA. Okay, so atomic weight we're given, N is the number of atoms inside the unit cell, which you must remember, guys, from the table. We're going to refer it back. VC is the unit cell volume, okay? And NA is Avogadro's number, okay? So what we want to understand now is we want to find N and VC number, okay? And from the VC number, we can reiterate it in terms of R and then find R in terms of the numbers here. That's going to be our answer, right? So that's the strategy we want to follow. Okay, since this is a BCC structure, right? And your unit cell is simply a cube, which has height of A, length of A, and width of A, right? You want to define your A in terms of your radius of your vanadium, right? And this is exactly what we have in this table. It's called the lattice parameter. And I proved already to you guys that A, the length of your unit cell, is going to be 2R root 2, okay? And the number of atoms is 4, okay? So that's your N number, okay? So your unit cell volume, since this is a cube, is simply going to be VC equal to A cubic, okay? And since your A is equal to 2R root 2, okay, you input it into your V, into your unit cell volume. That's going to be 2R root 2 cubic, which is going to give you 8R times basically 2 cubic, okay, R. So that's basically 2 root 2, so we can reiterate it as 16 R, that's R cubic root 2. Okay, so that's your unit cell volume. Okay. Oh, shit, sorry, you're right. BCC is 4. Sorry, I was looking at the FCC. My bad, guys. Sorry. Thanks for catching the mistake. But yeah, if it was the FCC, that would be the approach that you would do. Okay, yeah, thanks for catching the mistake. Yeah, this is a BCC structure. Sorry, guys, my bad. So this is going to be this guy. Okay, if it were the FCC structure, you would use the A value and the parameter here. Okay, but yeah, thanks for catching the mistake. That's 4R over root 2 for BCC crystal structure. Okay, so that's going to be 4R over root of 3. So A cubic, okay, that's going to be 4 cube R cube divided by 3 cubic here. Okay, that's your VC. your N is going to be equal to 3. Okay, that's what a BCC crystal structure has. They have only they have only 2 atoms inside your unit cell. So your N number is 2. Okay, so your N number is 2. Okay, so please memorize all those numbers. Lattice parameter, the coordination number, the amount of atoms in your crystal structure, unit cell. For BCC, it's 2. The lattice parameter is 4r/√3. So we're pretty much given everything now. The Avogadro's number you can write down in the given, guys. That's going to be 6.022 times 10 to the power of 23 mole to the power of -1. Okay. So plug it in back into your density equation. So density is equal to NA, weight, divided by 4 cubic r cubic over √3 cubic times your Avogadro's number. So from here, you can isolate for r and basically find your radius based on the other numbers because you're given density, N, AW, and Avogadro's number, right? So the final equation for r is going to be cube root of 3√3, okay, and A of atomic weight divided by Avogadro's number times 64 densities, okay, 64 times density. So that's your final equation for R. I'm not gonna solve this. You can do it in your own, guys. Let's not waste our time. So that's the final equation for your R, and that's the radius of vanadium. Okay, so that's how you simplify your radius of vanadium based on your given crystal structure, on your density and atomic weight. Okay, so you can like have different possible versions of this question. So make sure you memorize the stabilizing set. It's very important. Okay, memorize your number of atoms, your lattice parameter. Okay, so on the midterm question, you might be given like something like that to find basically the radius of magnesium atom or something else. Okay, that's similar to experiment number 1 in MTL200 course, when you have to find, in one of the questions, you have to find the radius of some atom. So that's like the same strategy that you have to apply. Okay, any questions on this, about this question? Anything else about here? No questions, no. Okay, I guess I will move on. All right, let's work on question number 2, and after which one we will jump into the Bragg's law equation, or actually the planar density equation question, and then we're going to jump into the Bragg's law question. When will this recording be posted and where it will be? I'm going to post this recording on the YouTube channel, and this link is going to be on my website. Okay, during our break, I'm going to post my website again. Okay, you'll be able to find my link there. Okay, let's do question number 2 now, guys. All right, so zirconium has an HCP crystal structure. Okay, so we have an HCP structure. We have a density of 6.51 grams per centimeter cubic. Okay, we have a volume. Okay, so we have that, blah, blah, blah. Okay, so we want to find the volume of the unit cell in cubic meters. Okay, we want to find the volume of the unit cell. And secondly, we want to, so this is, since this is the HCP structure, we want to find the height versus the base length ratio. Wait, no, that's given. We want to find the height itself and the base length also. Okay, so since we're given that this is 1.593, we want to find our C and we want to find our A. Again, you will not be likely given any HCP questions in your midterm, but we can do it just for the practice, okay? And this is like also important to remember. Okay, so solution, let's write down the solution. So you're given your density equation, and density equation is like the most important equation in this chapter. So let's rewrite this again. So first step, density is equal to number of atoms times atomic weight divided by your Avogadro's number times your unit cell volume. Okay, so from here we can isolate for unit cell volume. Okay, VC is equal to N times atomic weight divided by density times Avogadro's number. Okay, so you can plug in your values here and you will get your unit cell volume to be, let me take a look at the answer, 1.396 times 10 to the power of negative 28 meter cubic per cell, per unit cell, okay? So that's your unit cell volume. Okay, so now let's find the parameters of C and A. Okay, so since this is HCP structure, let's refer to our HCP structure here. Since we know that our base lengths here, basically A, is equal to 2 radiuses of our atom. Okay, so please memorize those values. So A is equal to 2R. Okay, so since A is equal to 2R, you can find the unit cell volume in terms of your radiuses, right? In terms of your A and C parameter, because like you have one equation and you have two parameters, right? You need second equation to find both parameters, right? So basically, let's go back, take a look. We know that our unit cell volume is 24 root 2 R cubic. Okay, so our unit cell volume can be defined by 24 R, what did I say there? 24 root 2 R cubic, okay. Root 2 R cubic. Okay, so you can plug this in, you can isolate for R. That's going to be A over 2. So when you plug this in, you will get 24 root 2 A over 2 cubic, okay? And you know with that value, you can find your A since you already found your unit cell volume, okay? And when you find your A value, right, you simply say that C is equal to 1.593 times your A value, and you will be able to find your answer. So you'll have A, then you'll have C, okay? That's pretty much simple question, okay, guys? Any concerns, any questions about this solution? No, quite straightforward. You have like equation and you have table you have memorized, okay? All important parameters of your unit cell structures, okay? Okay, I assume it's a no. Let's move on to actually question number 6. So that's the planar density for BCC, okay? So let's quickly recall what is a planar density. So planar density is, if you want to find the planar density, you want to find how packed your plane is with atoms that the plane intersects inside your unit cell, okay? So planar density is defined by the number of atoms centered on the plane divided by the area of plane. Okay, so let's read this question. Derive planar density expressions for BCC 100 and 110 planes in terms of the atomic radius r. Okay, so in here we'll basically derive, okay, we'll derive the planar density, okay, for BCC crystal structure. So part A, we have a BCC crystal structure. So let's draw the unit cell volume, the unit cell geometry here. Okay, so how does BCC look like? Let's take a look beforehand. So our BCC is like that. We have a one central atom, and we have 8 1/8 of the spheres. Okay, we have a large sphere inside, and 8 8s of spheres on each corner. Okay, the first plane we want to derive our planar density is 1 0 0. Okay, so let's quickly recall 1 0 0. Okay, you want to take a reciprocal, that's going to be 1 infinity infinity. Since this is all positive, okay, you define your origin is here. Okay, your 1 is here. So an infinity, so it's parallel to z-axis and parallel to your y-axis. Okay. Yeah, sorry. So this is going to be 0. This is your 1. And it's parallel to z-axis and y-axis. Okay. So this is your plane we're talking about. Okay. This is the plane. So this is like a front plane of your unit cell. Okay. So planar density, I have to emphasize, planar density is two-dimensional. Okay, so it's a zero thickness plane that exists and intersects the unit cell. Okay, so let's go back, take a look at the BCC crystal structure, right? So this plane is located right here. Okay, so this is the plane 1, 0, 0, and let's cross this out. Okay, so as we can see that this plane 1, 0, 0 intersects our unit cell, and it involves the area of 4, basically 8 of spheres, okay, on each corner of our plane right here. So let's rewrite this in our question. So the first step would be to define your plane, okay, and then you understand that your BCC. Okay, let me quickly erase that. Okay, so your plane intersects, okay, it intersects your structure, and it involves the areas of these 4 corners of your atoms, okay? This, and this. Okay, so this is radius of R, and this is correspondingly R and R. Okay, so again, let's now recall what is the planar density equation. Planar density equation, let's go back, is the number of atoms that are centered on a direction vector. Okay. Oh, sorry, that's for LD. For PD, for the planar density, it's the number of atoms centered on a plane. Okay, so number of atoms centered on the plane. Number of atoms centered on plane divided by the area of your plane. Okay, so we need to define 2 things: area of plane and number of atoms that are located on this plane. So regarding the number of atoms, let's start. Number of atoms is going to be easy. Let's start from the area of a plane. Okay, so area of a plane is an A. And since we know that the lattice parameter of a BCC crystal structure is 4R over root of 3. So again, you have to remember these values for the midterm because you will not have time to derive and all of that. Okay, so this is our unit cell parameter. Okay, so let's scroll down. Your area of your plane is going to be simply A squared. Okay, area of plane. And why is that so? It's because your plane has the lengths of A and height of A, because it's a unit cell, it's a cube, right? You have in A. So area of plane is simply A squared, so it's going to be 16R squared divided by 3. Okay, now regarding the number of atoms. So as I said, we're looking at the 2-dimensional now plane. Okay, so let's redraw this. Okay, 2-dimensional. So your atoms and everything you observe now is going to be 2-dimensional, not 3-dimensional. So in here, we're not talking about the spheres anymore, okay? Because if you have a sphere that is 3-dimensional, if you make a section cut, right, and you will get a circle, okay? You will get a circle. Okay, so in this plane, 2-dimensional plane, you do have basically this part of the sphere, this part of the circle. So this part of the circle, this part of the circle, this and this. So it's a quarter of the circle, right? Because if you were to take a look and section it, this is one of the sections, section. So this is 1/4. This is 1/4. This is 1/4 of your circle. And this is 1/4 of your circle. Overall, there are 4 1/4s. Okay, so the number of atoms is 4 multiplied by 1 over 4, which is 1. Okay, so in this plane, there's a full 1 atom, 2-dimensional atom. Okay. Any questions about that? Any concerns, anything? Okay. Thumbs up, understand? Yeah, all good. I suppose, yeah, okay, good. So number of atoms, again, 2-dimensional. You're not looking any longer at 3-dimensional sphere. As soon as you're talking about planar density, it's going to be a plane, okay? And the plane intersects, and you do have 1/4 here, 1/4 of the circle, 1/4, 1/4, overall 4 quarters, which gives you one full atom, okay, in 2 dimensions. So now we can calculate our PD, planar density, which is 1 divided by 16r squared over 3, which is 3/16 1 over r squared. Here we go. That's our planar density. That's it. That pretty much solved the question for only one plane, 1, 0, 0. Okay. Any questions on that? No. Did you understand it, guys? Just like type in the chat yes or no. So some feedback will be good. What does it mean by expressing in terms of r? In terms of the radius of your atom. Okay, because you're not given like the element. Okay, so let's say it was magnesium, right? Then you would plug in the radius of your magnesium atom inside the planar density here. So it would be like, I don't know, something meters, right? And then it will give you the value of the planar density pretty much. So in here, and we're working in terms of parameters, so you just use R. Okay, so your planar density value. Okay, any other questions? No? Okay, cool. So let's now determine the planar density for 1, 1, 0 plane. Okay, so that's going to be a little bit complicated now. So 1, 1, 0, let's construct, I don't have space here. I'm going to use question 8 as my space for now. Okay, so that's going to be part A2. Okay, so we want to find right now the planar density of 1, 1, 0 plane. So the first step will be to draw basically your plane like that. Okay, and we do inverse of that, so 1, 1, infinity. Okay, so we know that every number is positive, right? So you have 0 here, you go 1 in x-axis, 1 in y-axis, and infinity to z-axis. So it means that you have a diagonal plane. Okay, so what these questions would be examples of the short answer in the midterm of the multiple choice. You might get planar density question, because like honestly, this question is not that complicated, and especially if you're talking about like 0, 0, 1 plane or 0, 1, 0 plane, you might be asked to like define and find your planar density, right? And then later you're going to be like given R, so you just plug in your R here and that's it, right? This question is not that complicated, just I'm taking my time to explain it to you. That's why it like takes a lot of time for this, but it's actually pretty straightforward, okay? So it might be one of the questions in the midterm, so be careful, or final exam, okay? So make sure you practice that, okay? So 1, 1, 0 is going to be always diagonal section, okay, of your unit cell. So diagonal section is that. And since we're talking about the same crystal structure, BCC, let's refer back to our BCC crystal structure. So I would suggest you also guys to memorize how your BCC, how your crystal structures look like, right? Just one has one full atom inside, one has semi-spheres, hemispheres, right? This is just like 8 of spheres, yeah. Just like memorize it visually, okay? So when you create your diagonal plane here, okay, you will see that your plane will be intersecting a lot of stuff, okay? So let's now write down again the equation of planar density. So planar density, number of atoms that the plane contains divided by area of plane, okay? So our area of plane is not going to be no longer a squared. Okay, it's going to be a little bit different. Okay, so since this is a and this is a, okay, and this is a, this is a unit cell, we can observe this triangle. Okay, so this triangle is going to be a, and basically by Pythagorean theorem, you will see that this is a root 2. Okay, so this is a root 2, and this is a. So the whole plane is a and a root 2. So area of the plane is a squared root of 2. Okay. In BPC crystal structure, oh sorry, BCC, we have IA equal to 4R over root of 3. Okay. So when you plug in your 16R squared root of 3 divided by 3, that's going to be your area of your plane in terms of your R. Okay. Now, let's define how many atoms are intersecting the that's the 110 plane intersects in BCC unit cell. So that's going to be complicated to visualize, but so again, let's refer back to our BCC model. Okay, BCC crystal structures right here. So as you can see, the plane will intersect, again, two-dimensionally, this ace of the sphere, this whole atom, okay, and then it will have just in four corners, it will have atoms in each single corner of your plane. Okay, so if you were to draw on your plane the atoms that it intersects, it would be pretty much like that. Okay, so that's a two-dimensional look, a section cut, just like imagine your section cut in your unit cell. So yeah, and now you will need to calculate the amount of atoms. So again, keep in mind, you're no longer looking at three-dimensional plane, it's a two-dimensional plane. So a circle is defined as one atom. So one circle is atom. Okay, so in here, we do have number of atoms to be 1 plus 4 times 1 over 4. So again, those are quarters of the circle, right? So there are 4 of those. So now you have 2 atoms. Okay, 2 atoms. So planar density is simply going to be 2 divided by 16R squared root of 2 multiplied by 3. 3 goes here, so it goes up. Okay, so 2, 8. So you will get 3, 8 root of 2, 1 over R squared. Okay, and that's the answer to part A. Okay. So the planar density of 110 in the BCC plane will be 3 over 8 over 2 times 1 over R squared. Okay, so that's the planar density for that plane. Any other questions? Any concerns? Anything else? Can you explain how you found the area again? Yeah, sure. So first of all, you need to understand that you have your 110 plane, right? Your 110 plane is as diagonal, right? So you just use your Miller indices and you use the approach that we defined before when we were looking and having practice into the like the Miller indices and planes, okay? So 110 is just a diagonal plane. Right? So that's the first step that you have to understand. Secondly, right, in order to find your planar density, you need to understand that you also need to find the area of your plane, okay? Area of your plane and how to find it, okay? So you draw your unit cell, okay? And you put this section plane there. And you can see that from your unit cell, your sides are all A, okay? Your lattice parameter. But your unit cell goes diagonally, okay? So you will need to observe like from the top. Imagine you're looking from the top, right? So from here, let's say, this is going to be like A. You can form a triangle. So that's going to be A, and you need to find this diagonal. Okay, so A squared plus A squared is equal to 2A squared. So that's your diagonal. So your diagonal is A root 2. Okay, and in order to find your area of your plane, you need to multiply this side by this side, right? So it's simply A times A root 2, which is A squared root 2. Okay, does that make sense to you? Any confusion on that? No? Makes sense? Okay, cool, perfect. Should be good. All right, any other questions? No? Suppose no. Okay. Write something in the chat, guys, so that like I can see some feedback, okay? Is A square root 2 always going to be the denominator? Yes, that is correct, because your area of your plane is always in the denominator. That's going to be always in your... Oh, good, thank you. Perfect, awesome. Thank the review is awesome. Thank you. I appreciate that. Thank you guys for the feedback. Awesome, awesome. All right, let's now jump into the questions of the Bragg's Law. And I can guarantee you will have some Bragg's Law questions. If not, that's going to be kind of weird. But usually on each midterm, there's going to be at least one Bragg's Law question. Okay. So let's do that. Let's do this question. I'm going to do only one question because we're like, Jesus, like one chapter we have covered so far. Okay. So let's hurry up a little bit. But that chapter is complicated, not gonna lie. Like there's a lot of stuff you have to memorize only from chapter 3. Okay, so it's good that we're taking our time looking into it. Okay, so that's question number 7 on my study hall notes. So, all right, let's read the description. How did you do in your midterm? On my midterms, like which midterms? The ones that I had in my 3rd year just now, or you're asking about MTL200 midterm? Oh, your midterms this year? My year is quite brutal. I'm in my 3rd year of aerospace right now. Yeah, it's like the hardest year, the hardest semester, I would say. I did it quite okay, yeah. Interesting courses, good profs. So yeah, I did quite well. But yeah, anyone from aerospace, reach out to me. I can give you some hints, you know, for your 2nd and 3rd years. So yeah, reach out to me. How much do you study daily? Oh, I study a lot, like a lot, very much. Yeah, I can dedicate like decent like 16, 17 hours just like in one day just studying straight. It takes a lot of concentration and discipline, which I do have, which I would suggest you guys also. More discipline you have, more concentration, the better you're going to do in your midterms. Okay. So yeah. Anyhow, let's jump into the question. The metal iridium has an FCC crystal structure. If the angle of diffraction for the 220, okay, you're given here a 220 plane. And you're also given the crystal structure. Okay, so like when you read the question, pick out like the key points from the question. Okay, so if the angle of diffraction for 220 set of planes occurs at 69.22 degrees, when monochromatic X radiation having a wavelength of 0.1542 nanometers is used, compute the interplanar spacing for this. Oh yeah, so DHKL is interplanar spacing. Here we go. I've just remembered. So let's go back. So this question actually reminded me, yeah, DHKL is interplanar spacing. Okay. Interplanar spacing. Here we go. Exactly. Okay. Okay, let's scroll down back to the question. Get at the next chapter. Okay. Yeah. Let me remove that. Here we go. All right. So, and B, we have to find the atomic radius for an iridium atom. Okay, let's write down what we're given. Okay, so clearly it's a Bragg's law question because you're given like X radiation and blah blah blah. If you're asked about radiation, it's going to be like definitely a Bragg's law equation you have to implement. Okay, so all right, we're given FCC crystal structure. We're given 220 plane. Okay, we're also given. So first order reflection means that n is equal to 1. Remember when I was talking about the Bragg's law question, somebody asked me about what is n. So this is the order of deflection. Okay, so it's usually specified, might be not specified. If it's not, it's just 1. If it's 2nd order, it's going to be n equal to 2, and it might be like many other orders. Okay, so n is equal to 1 because it does specify is like first order reflection. Okay. And 69.22 is going to be our angle. Let's call it alpha for now. I'm going to be talking about that a bit later. Angle is tricky. Okay, there's going to be a quick hint for you guys. And we are given also wavelengths. Okay, wavelengths is 0.1542 nanometers. And also keep in mind, nano is 10 to the power of -9 meters. Okay. All right. Okay, what are we looking for? So A is going to be to find our D of 220, DHKL, okay, interplanar spacing of 220 plane. So basically it's how far each single 220 plane is from each other, right? Because in one unit cell, you have your 220 plane, in the other unit cell, you have two zero planes. So you want to define this perpendicular distance between two planes. Okay, so how far each plane is from each other. Okay, so part B is to now find the atomic radius for an iridium atom. Atomic radius is just R. Okay, solution. Let's now find out what is going to be our DHKL. So clearly DHKL we can find from the Bragg's law equation. So let's take a look at that equation, which is n lambda is equal to 2 DHKL sine theta. Okay. So let's keep it concise. N lambda is equal to 2 DHKL sine theta. Please memorize this equation. Most likely it's going to be given on your equation sheet. If not, please memorize it. Okay, 2 DHKL sine theta. So we're given n, we're given lambda, we're given so angle. Angle is important to understand. Okay, so what is our theta? Because this is the trick, and this is like a trap that basically everyone, like 50% of students, even 60, basically got into last midterm. They just put 69.22 angle into their equation, and they thought they were done, but it's not correct. Because if you understand how the Bragg's law works, yeah, it's 2 theta, correct? Yeah. So what happens basically when you put your sample into X-ray machine? In a 3-dimensional space, what happens is you have a conical like a conical interception of your film. So if anyone had experiment number 2, you do have on your like on the strip, you do have like arcs, right? Those arcs are 2-dimensional, but in 3-dimensional plane, what happens is a cone. Cone intersects those strips and it forms those arcs, right? Because like if you intersect a cone, right, it's going to be like a triangle pretty much. And since this is a circle, because your strip is wrapped around inside your inside the element where you put your sample in, right? So if your sample is right here, right, then your strip, so let's say this is your strip from your experiment number 2 or 3, it's called X-ray diffraction, right? So this angle which is given to you is your alpha, okay? But the Bragg's law equation only is concerned about your theta, okay? And alpha is equal to 2 theta, okay? Please everyone understand that. It's a trap that like a lot of students lost the marks, you know, here. So you have to divide the given angle by 2, okay? And then put it into your equation, okay? So you're only concerned about this angle theta here in Bragg's law question, okay? So whatever angle you're going to be given, divided by 2, please, okay? So any questions on that? Please memorize the angle you're given. Please divide it by 2. Don't make this mistake, okay? So I guess no concerns on that. So we're good. All right. So simply, like the question is so simple. Like just like conceptually, you have to understand that the angle you're given will have to be divided by a factor of 2. That's it. So D220 is equal to n lambda divided by 2 sine theta. Okay, so that's going to be theta is equal to alpha over 2. Okay, so that's after you plug in all your numbers, that's going to be 0.1357 nanometers. Okay, so again, 0.1357 nanometers is just the distance between 2 to 0 plane in your crystalline structure. Okay, between the 2 to 0 planes. Okay, now you need to find the radius of your atom. Okay. So let's say this is part B now. It's isolated. Okay. So for part B, you need to find the radius of your atom. Okay. So now we have to refer to the second equation that we had. And the second equation was about the DHKL. Okay. So this is the lattice parameter divided by h squared plus k squared plus l squared. Okay. So right. So our D is equal to A divided by H plus K plus L squared. All those are squared. So we know what is H, we know what is K, we know what is L. Okay, so you can simply find your A by multiplying D times square root of 2 squared plus 2 squared plus 0. So just that. And that's going to be 2 root 2. So 2 root 2d, right? And you plug in the value of d here, and you will get your a as 0.3838 nanometers. Okay. And from there, you know that you're given FCC crystal structure. So FCC, it means that your A is going to be equal to 2R root 2. Okay. Yeah, so basically you didn't have actually to do this calculation. What you could have said is that 2 root 2D is equal to 2R root 2. 2 root 2D is equal to 2R root 2. And you can cancel out 2 and root 2s. And you can deduce that D is equal to R. So your interplanar space is equal to radius of your atom. Okay, that's simple. And that's it for the Bragg's law question. Okay, do we need to solve for A or is it D? Okay, like you don't have to solve for A. For D, you have to, because you have to find D. It's part of the question. For R, you need to solve just for R. You don't have to solve for A. What I did is just said it's 2 root 2D. Okay, and since from the crystalline structure, from the unit cell definition, A is equal to 2R root 2, and then you can just equate your 2 root 2D is equal to 2R root 2, which is just D is equal to R. Can I explain part B again? Yeah, sure, I can. Perhaps I can get some better space here. Okay, so let's start part B here again, okay? So let's say you found your DHKL, okay? You're given that your DHKL, whatever you found there is 0.1357 nanometers. Okay, DHKL, which is D220 is equal to 0.1357 nanometers, right? From your equation, you know that D220 is equal to A divided by square root of HKL, right? In your equation, you have H squared plus K squared plus L squared. So it's 2 squared plus 2 squared plus 0 squared. Okay, so this will give you A divided by 2 root 2. Because this is 8, the root of 8 is 2 root 2, right? So you want to find R, right? So the way to find your R is from your lattice parameter, okay? Because you know that for your FCC, so since FCC, then you know that your A is equal to 2R root 2, okay? And then you just simply plug this back in here, and you find that your D220 is equal to 2R root 2 divided by 2 root 2. So numbers cancel out, and you're going to be given as R, 220. Okay, and since those are the same, then there's going to be just 0.1357 nanometers. Any concerns about that? Any questions? No? Thank you. Sure, my pleasure. Okay, perfect. We're done with this chapter. Okay, for the rest, there are a lot of sample questions, practice questions. Please do it on your own. If you have any questions, please let me know. I will be more than glad to answer those. Okay. Anything about chapter 3? Any questions before I jump into chapter 4?
Are these questions we're doing in the same form that they might come on the exam?
Yeah, so especially like the Bragg's law question might be similar. Yeah. Might be similar.
Okay, thank you.
Last year, remember, it was same concept. Make sure you practice question 8. I do remember it was also a similar question. They were like either question 7 or question 8 were like similar questions in the midterm, I remember, yeah. Yeah, so make sure you practice that. So this question was quite interesting, number 8, because you will have to refer to this table. Okay, and that's what I'm saying. You must memorize this table because actually I believe the question 8 was like on the midterm last year. Okay, so practice that for sure. Make sure that like you understand all of that. Okay. Well, you know what? Actually, it's a simple question. Let me like just walk you through really quickly so that you don't like suffer on your own. Okay. Let me clear this out. Okay, so you might be given this question 8 on your midterm, so I'll just quickly show how to approach this question. Okay, Okay, perfect. Do we convert nanometers to meters? Depends on your question. You might be left with nanometers as the answer, maybe on meters. Okay, that's why I put down this conversion unit. Okay, 10 to the power -9. But most likely it's going to be nanometers. There's also Armstrong, like that. That is 10 to the power -8 centimeters. Okay, also remember that. Sometimes your radiuses might be like in Armstrong, you know, or something like that. Yeah. So in your lab, whoever took experiment number 2 again, or 3, I don't remember, the X-ray diffraction, there was like Armstrong. So yeah, they use this unit there. But like anyway, question number 8. For which set of crystallographic planes will a first order diffraction peak occur at a diffraction angle of 46.21 degrees for BCC iron when monochromatic radiation having a wavelength of 0.0711 nanometers used? Okay. So it might be complicated. So without this table, you will not be able to solve this question. Without this table, without this knowledge, okay, you will not be able to solve this question. So you have to memorize this table. Okay. So let's do this question. Let's see what is given. So we have alpha of 46.21 degrees. We have BCC crystal structure, monochromatic radiation having a wavelength of 0.0. So we have lambda of 0.0711 nanometers. Okay, and we want to find HKL. Okay, so solution. Okay, so what we want to do is we want to find our DHKL, right? So the only way we can determine our HKL is obviously from here, right? So this is the only mention of HKL values that we have in our entire chapter here. Okay, so obviously you will have to find this, and from there you will have to go here, okay? So let's find what this root is, square root of h squared plus k squared plus l squared, okay? So again, let's write down our Bragg's law equation, and lambda is equal to 2 DHKL sine of alpha over 2. Again, don't forget your alpha is 2 theta. Okay. So DHKL is n lambda divided by 2 sine of alpha over 2. And if you plug in all your values, you will get 0.0906 nanometers. Okay. Okay, cool. You know that DHKL at the same time is equal to a divided by square root of h squared plus k squared plus l squared. Okay, so from here you can find your square root of h squared plus k squared plus l squared, which is a DHKL. Okay, and your a, okay, so what is this? BCC iron. So we are given that this is a BCC crystal structure. Okay, so in this question, we're not given the radius of your iron, but in the midterm, you would be given radius of your iron. Okay, so radius of your iron would be equal to 0.1241 nanometers. Okay, so like, don't worry, you're going to be given the radius of your iron. You don't have to memorize those values, so you're going to be given that. So since this is 4r over root of 3 for BCC, right? When you like plug in all the values, your root of all of that is going to be equal to 3.163. Okay. So here, when it's going to be quite tricky, right? We have to determine what is our HKL. Okay. So let's square it. Let's square it in order to get rid of the square root. And that's going to be 3.163 squared, right? Which is going to be like close to 10. That's going to be close to 10. So you don't need to use calculator for that. Okay, just say it's close to 10, because 3 squared is going to be 9. Okay, but since you have 0.163, when you will square that, you'll determine that this is going to be quite close to 10. Okay, so let's refer back to the table. Okay. So our H, K, and L we know that this is BCC structure. So in order for H, Cal, K, and L to be equal, of those squared to be equal to 10, sorry, is it not A over D? Oh yeah, sorry, I actually made a mistake here. Sorry, my bad. Where is it? Yeah, I isolated for HKL squared incorrectly. It has to be A divided by DHKL. Yeah, thank you. Anyway, the answer is going to be that. Okay, 3.163. Okay, so A is that. Yeah, good catch. Thank you. So anyway, getting back to it. So our H squared plus K squared plus S plus L squared is equal to 10. This is given. We also know that this is BCC. Okay, so what you must memorize from this table is that for BCC crystal structure, the reflections present are always give us A, H plus K plus L to be even. Okay, so the whole sum must be even number. Okay, so the only possible way that our HKL to satisfy the condition that H plus K plus L is equal to even, and also H squared plus K squared plus L squared is equal to 10. Okay, so you just like do, you just like, you know, try it out, trial and error method. Okay, so let's pick 1, 1, 1, 1, 0. Okay, so if we plug in 1, 1, 0 to this equation, this will be satisfied. It's going to be even number 2. But if we plug it in here, it's going to be 1 squared plus 1 squared. That's going to give us only 2, which is not equal to 10, right? So that doesn't work. Okay, let's do more. Let's put 2, 2, 0. Okay, so if you put 2, 2, 0, even is going to be satisfied condition. But it's if it's H squared plus K squared plus L squared, it's going to be 4 plus 4 plus 0 is equal to 8, right? Which is not 10. So we cannot have 2, 2, 0 plane. Okay. Let's try another method, another Miller indices combination. Let's try something like 3, 3, 3, 0. Let's try 3, 3, 0, right? So that's going to give us even, but that's going to be overshoot, right? 9 plus 9 is going to be 18, so that's not correct. So let's play with this number now. Let's try 2, right? 9 plus 4 is 13, incorrect. Let's put number 1 here. Okay, so we have 9 plus 1, which is 10, and 3 plus 1 is 4, which satisfied the even condition, right? So we chose basically the Miller indices by trial and error, which will satisfy the answer of the question. Okay, so 3, 1, 0 indeed works here, indeed works here, so perfect. So the answer in terms of the arrangement of Miller indices, it doesn't matter. It can be 0, 3, 1, 0, 1, 3, it doesn't matter. What's going to be marked is, well, on your ABCD, you'll be like given like AB question, like one of the possible variations is going to be there. So you just have to make sure you have 3, 1, and 0. That's it. What's the hardest chapter for you? Hardest chapter. I don't know. I've been like working in material science field for quite a while. All the chapters seem to be easy. I'm working in Dr. Ravi's lab as a research assistant and working on a lot of research projects. So like I've been, you know, this is like the basics of the things that I have to know. But back in my first year, I remember chapter 9 was complicated, like the phase diagrams. I remember that. We're gonna cover it today. How did HKL equate to 10? So you find your DHKL value. Okay, you find your DHKL value, after which you find the square root of H squared plus K squared plus L squared, which is equal to 3.163. So if you actually try to square it, you will get something close to 10.004569. Okay, so you get rid of the square root, you will have H squared plus K squared plus L squared is going to be equal to 10, close enough to 10. Okay, and then since you know this is your BCC condition, you just put those in the systems of equations and you want to satisfy both conditions, and that's it. Okay, any questions on that? Are we good to move on the next chapter now? Thank you. Yeah, I guess everyone is good to go for next chapter. Okay, chapter 4. Yeah, sure. Imperfections in solids. Okay, so in the previous chapter, we defined our crystalline structure to be a perfect model of our metal. Okay, so we have a crystal, we have a unit cell, and this unit cell propagates throughout the whole metal. Okay, it's the same, it's repeating itself, and this model is perfect, okay, and it's working. However, in reality, you always have some defects, okay? You always have, in your metal, you will always have voids, porosities, you will always have some mismatches, atomic mismatch. So in reality, it's a total mess. Like you will never ever find actually a perfect unit cell inside your atom, okay? So in this chapter, we're going to be talking about simple, basic imperfections in solids. And this chapter is like theoretically like, heavy. So there's not so many equations to solve. There can be a couple of, a couple of equations, but we're going to do a couple of practices. It's going to be fine. So crystalline defect is the lattice irregularities. Okay, so again, imperfections kind of matter. So vacancies and self-interstitial. Okay, so I'm gonna like describe what is this. Okay, those are point defects. Okay, so there are point defects, and we're going to be covering another type of defects later. Okay, so what is substitutional and self-interstitial defects? Okay, so substitutional. So imagine you're looking from the top on some array of atoms on your plane. Okay, you have this atom, this atom, this atom, like these atoms. Okay, so substitutional is going to be something. So let's say your structure is missing one of the atoms. Okay, so another foreign atom will be able to go in here. Okay, and if this atom is satisfying certain conditions, which we're going to be talking about later, this is going to be a substitutional vacancy. Yeah, substitutional vacancy, which is a point defect. Okay. So again, if you're missing an atom, substitutional vacancy, okay, basically that's what it means. Okay, your interstitial vacancy. Okay, there are a lot of interstitial vacancies here, like here, 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 here. So basically, if some small atom can go in between your large atoms, okay, that's called self-interstitial vacancy. Okay, which is also a point defect. Okay. Yeah, so we're going to be talking about those rules as well. So you just have to memorize what is the distinction between both. Okay, so substitutional is one atom which is missing from there, and another atom can go in there, and self-interstitial is between the atoms. Okay, so as we can see here, this is the vacancy. So one large atom is missing from here, and self-interstitial is when one atom goes in between those atoms. Okay, so here's an equation of the equilibrium number of vacancies equation. So NV is equal to N exponent of negative QV over KD, which is the same as NV over N. We're going to be doing practice questions on that. So here's just an equation. Yeah, this is a fraction of atom sites. We're going to be talking about this later. So substitutional and self-interstitial point defects are found in solid solutions. And just a quick note. Okay, let's talk about the Hume-Rothery rules. Okay, those rules are going to be on your midterm for sure. You have to memorize those 5 rules. Okay, so atomic size factor, crystal structure, valencies, and maximal allowable interstitial impurity. So please memorize those instructions, rules. Okay, I'm not going to be reading this, but like please remember that. Okay, so numbers are important, plus minus 15%. That's for, yeah, so this type of solution, blah, 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 between the two atoms is less than 15%. 15%, less than 10%, memorize these numbers. Electronegativity factor. So in your midterm, you might be asked, like, is electronegativity factor a part of the Hume-Rothery rules or something like that? So just make sure you remember this. You remember this is very important, okay? Hume-Rothery rules. Okay. Okay, specification of composition for 2-element alloy. Okay, so this is like a set of equations that allows you to transfer from weight percent to atom percent. Okay, all of those questions are like related to each other. So let's say you're given atom percent, and you want to translate it or like to weight percent or vice versa, okay? Or you want to translate it from weight percent to mass per unit volume. Okay, so you just have this set of equations. And based on that, you can define your average densities, okay? Those are the equations. Those equations are going to be given to you in your equation sheet, okay? But still practice, make sure what is which, okay? Right, okay. So when we have point dislocations, okay, so those are like just one-dimensional point defects called substitutional and self-interstitial defects. You also have so-called line defects, okay? So you have, in this course, we're discussing 1D and 2D, okay? So point defect and line defect. Of course, there are 3D defects, which are related like on a plane that gets crazy there, okay? So the linear defects are dislocations, and this is when we start mentioning the Borger's vector, okay? So dislocation, linear or non-linear defect. So please make sure you understand those concepts here. Borger's vector, mixed dislocation. Yeah, so Borger's vector is the magnitude and direction. So on the midterm, you might be asked, is the Borger vector only magnitude or direction, or is both, okay? Or none of the above, pretty much. So yes, Borger's vector is the magnitude and the direction, okay, of the lattice distortion. Edge dislocation line, blah, 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 blah. That's from textbook. So what you have to remember, which is very important, okay, I highlighted it here, might be asked in your midterm. So Borger's vector is the same at all points along its line. Make sure you remember that. Borger's vector is perpendicular to the edge dislocation and is parallel to the screw dislocations. Okay, just memorize it. Okay, if you're interested in what edge dislocation, screw dislocation is, read the textbook, please. I'm gonna like spend a lot of time explaining what that is and visualizing it for you guys. Please read the textbook. But I would say it's good enough to just like remember that the Borger vector is always perpendicular to the edge and parallel to the screw dislocation. That's going to be like probably one of the midterm questions for sure. So please remember this, okay? Also, Borger's vector is neither parallel or non-perpendicular to mixed dislocations. Quite obvious, okay? So metallic properties, magnitude of the Borger's vector in a closed path direction is equal to your interplanar spacing. Also memorize this, might be one of your midterm questions, okay? So let's talk about interfacial defects. Those are kind of three-dimensional defects, super complicated. We're just talking about like the concepts of it, you know. So interfacial defects are boundaries that have two dimensions, and normally, okay, so this is still two-dimensional. Sorry, those are boundaries that have two-dimensional or normally separate regions on the material that have different crystal structures or crystallographic orientation. So basically, it's like crystallographic mismatch. Imagine you have one unit cell of one crystal structure, another unit cell of a different crystal structure, and the interface between both is going to be like some mismatch. Okay, that's going to be like interfacial defect. So there are external surfaces, grain boundaries, phase boundaries, twin boundaries, and stacking faults. So please memorize this small summary in the green box, especially twin boundaries. It was questioned last semester on the midterm. So twin boundaries are only seen in mirror lattice symmetry due to atomic displacement from applied shear forces is only seen in BCC and HCP, and the annealing after deformation happens on only FCC. Okay, just like memorize it, might be asked in midterm. Okay, a lot of midterm questions are going to be random like that. Okay, just like a super specific, theoretically, conceptually heavy questions. Okay, so whatever I have in those boxes, you better memorize all of that. Okay. And stacking faults occur only in FCC crystal structures, okay? Also memorize it. Side note, as the packing density increases, the surface energy decreases, okay? So also interfacial energy does depend on the boundary type. So last semester, there was a question about Young's modulus and how it relates to the grain boundary, okay? So what you have to always remember is that the packing density, so the surface energy, it's like the nature always tries to possess the lowest possible energy level. Okay, so you always want to understand that the surface energy always wants to decrease, okay? And also interfacial energy does depend on the boundary type. Okay, so boundary type, how the grain boundaries intersect with each other. Okay, so they also affect the interfacial energy. Okay, that's why the water in the space always tries to be spherical, because sphere is the most efficient packed amount of space that water can occupy. So its surface, it wants to possess the least possible surface energy, the water in space. That's why it starts forming a sphere, right? So just one interesting fact for you guys. So let's talk about three-dimensional mismatches, which are called volume defects. Volume means three-dimensional. So you have pores, cracks, foreign inclusions, and some other phases. So not much into it. There is like a there is a chapter, not a chapter, but you can small paragraph in the textbook in the chapter. Make sure you read that. Might be a question about that. Might be a question like, what are the volume defects? And you have like A, B, C, D, which lists like these possible things. So make sure you memorize what are the volume defects, okay? Microscopes, you will have one question in the midterm about microscopes. So you have to remember which microscope corresponds to which magnification. So optical corresponds to the maximum of 2000 magnification. TEM corresponds to maximum 1,000,000 of magnification. Okay, and scanning electron microscope and scanning probe microscope, okay, which can form 3D images. Last year in the midterm, there was a question about scanning probe microscope. And yeah, it was like a question, which microscope can create 3D images, right? And it was like A, optical microscopy, B, TEM, SEM, SPM, or none of the above. Okay, so SPM was the answer, okay? So make sure you remember all the stuff here. So yeah, read 4.0 chapter. It discusses the microscopes, okay? It's going to be like one question for the midterm for sure. Okay, let's jump into the questions for chapter 4. Again, chapter 4 is not that theoretically heavy, so we're going to just do a couple of practice questions and then jump into chapter 5. Chapter 5 is going to be about diffusion, okay? So let's do a couple of practice questions here. Let's start from question. Let's do question 1, question 2. And then we're going to do one question that appeared last year on the midterm. Oh, that's going to be from chapter 5, yeah. Anyway, we're going to do two questions here, okay? All right, let's start from question 1. Calculate the activation energy for vacancy in formation in aluminum, given that the equilibrium number of vacancies at 500 degrees is that value. The atomic weight and density for aluminum are respectively 26.98 grams per mole and blah, blah, blah. Okay, let's write down what is given. So this question is about the activation energy. And in the first portion of this chapter, I discussed this equation. I just mentioned it. So this equation refers to the basically activation energy, which is right here. K is the constant. I forgot the name of this constant. If somebody remembers the name of this constant, please shoot in the chat. T is temperature, and NV over N is the fraction of atomic size. Okay, so this is that ratio. And this is the vacancy equation. So you want to find the number, Boltzmann constant. Yeah, here we go, exactly, Boltzmann constant. Yeah, thank you. So in this equation, you basically want to find what's the kind of maximum or average amount of vacancies that you can have inside your crystal structure, which is based on the amount of atoms that you have, your temperature, and your activation energy, okay? So given we have a temperature, so always make sure that you in this kind of questions, you always put your temperature in Kelvin, okay? Because your Boltzmann constant has the Kelvin in there, so it has to be absolute, okay? So 773.15 Kelvin. So temperature Celsius to Kelvin is, so temperature in Kelvin is temperature in Celsius, whatever you have, plus 1273.15 Kelvin. And that's the conversion that you have to memorize, guys. You have to memorize it, okay? You're not going to be given this conversion. So yeah, a lot of people, they made a mistake last year, did not converting this value to Kelvin. So the value was off and they couldn't find the answer. So so the equilibrium number of vacancy, so we're actually given NV. NV is equal to 7.57 times 10 to the power of 23 meters power of -3. We're given that value. The atomic weight and density for aluminum are respectively blah 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 blah. 26.98 grams per mole. We're given the atomic weight. So atomic weight is equal to 26.98 grams per mole. And the 2.62 is our density for aluminum. 2.62 grams per centimeters cubic. Okay. So calculate the activation energy. So we want to find our QV. Okay, so let's write down the equation. The equation that we mentioned before, right? So NV, N, I think it's a logarithm or something. Or yeah, it's exponent. Exponent. So e to the power of negative EQ, Q activation energy divided by KT. Okay, negative QV divided by KT. Right, so in here we are given almost everything, and the Boltzmann constant is going to be geez, what's the Boltzmann constant? Yeah, the Boltzmann constant is K. It's going to be given to you in the equation sheet. Okay, 8.62 times 10 to the power of -5 electron volt divided by atom Kelvin. Okay, that's your Boltzmann constant. So from this equation, in order to find your QV, right, we can isolate for QV now. Okay, so you can take a natural logarithm. Ln of NV is equal to, so when you take natural logarithm of that, it's going to be ln of N, right? Okay, and you will have times negative QV over KT, right? QV over KT. Let me double check that. Oh, sorry. When you do the logarithm identity, it's actually going to be plus. So it's going to be plus minus QV over KT. Let's not forget the logarithm rules. Logarithm of AB is equal to logarithm of A plus logarithm of B. Okay, so please remember that. Okay, so natural logarithm of NV minus natural logarithm of N. So if you move it to the other side, and V minus natural logarithm of N is equal to negative QV over KT. Yeah, so this is going to be right now NV over N. So identity of natural logarithms. When you have logarithm of A negative minus logarithm of B, this is going to be logarithm of A over B, assuming you have the same base here. Okay. So that is going to be equal to negative QV divided by KT. Okay. So what you're not given from here, so basically let's isolate for QV finally. That's going to be negative KT, natural logarithm of NV over N. Okay, what you're not given from here is only N number. All the rest you have. Okay, but number N you do not have. So how to find your N number? You'll have to use an equation. Okay, so if this equation is used in the textbook, right? So this is going to be NaRAl. It's a similar question of the density because you're given the density equation of the density, right? So I mean, it's the equation of the density, which is mentioned in the textbook. So after you reiterate it, so this is the density equation, which is always the number of atoms. So it used to be N for us, times atomic weight divided by by the Avogadro's number, times there's something else for chapter 3. Let me take a look. So the density equation, oh yeah, volume cell, okay. Volume cell, where's that? Here we go. Volume cell. Okay. So in here, in this equation, you assume that your volume cell is equal to 1 meter cubic. And this allows you to determine basically this equation. So a rho is equal to big N. So just put this N as a big N because the number of atoms in the activation energy question is this N, not a smaller N. But it's the same variable, okay? So N times A divided by NA times 1. So if you isolate for N, okay, you'll get NA times density divided by atomic weight. Okay, and this is the equation that we have here. Okay, so just a quick proof to you guys. So you just assume here the volume of the unit cell is 1. In the textbook, they might derive it more in depth, so just if you're interested, look at it. But that's the equation that you can use to find your number of atoms. Okay, so when you do that, you plug this in here and you just plug in all the values and you will be able to find your activation energy. Okay, so quite simple. It's just like plug and chug. Okay. So yeah, at the end, your answer should be negative, sorry, not negative, should be positive 0.75 electron volt per atom.
Sir, sir.
Yeah, yeah.
So you're saying the number of atoms is equal to the big N?
Yeah, your N, small n from your chapter 3 is equal to big N from chapter 4. Okay. Chapter 3, this is chapter 4. Okay. Any concerns about that? Do you want me to go over it again or it'll be okay?
Sir, I got another question. If you scroll
Yeah,
up
yeah,
to the
yeah.
first equation in chapter 4,
Yeah.
NV equals N and then exponent.
Yep.
When it says exponent at EXP, does it mean the E function? So N to the E
Yeah.
to the power of...
Yes, that is e to the power of something. Yeah. So exponent of 3 means that you have e to the power of 3. Okay. Makes sense, yeah?
Yeah, thank you.
Okay, cool, perfect. Any other questions? What is NV? NV is the number of vacancies. So how many vacancy atoms you can have in your structure here? Okay, so in here it's defined as the equilibrium number of vacancies. Okay, so QV is equal to 0.75. Yes, it would take 0.75 electron volt. This is the energy pretty much, electron volt. There's a conversion from electron volt to kilojoules, right? But you will not have to convert. Your answer probably is going to be in electron volt. So this is the amount of energy it takes per atom. Okay, this is activation energy, and yeah, you're given the NV as this number, which is the equilibrium number of vacancies. Okay. Okay, let's do now question number 2, and we're going to conclude this chapter. You can do the rest of the questions on your own. Okay. So question number 2, what is the composition in weight percent of an alloy that consists of 6% of atomic weight of lead and 94% of atomic weight percent of tin? So you're given that atomic weight percent is equal to 6% of, oh, sorry, my bad. We can actually call it maybe atomic percent of tin, or of the lead is equal to 6%. Of atomic percent of tin equal to 94%. Okay, and cool. All right. So basically what we're trying to do is to transform from atomic percent weight to weight percent. Okay. So we want to find weight percent of lead and weight percent of tin. Okay. So you're going to be using the equations from here. Okay. So I would suggest you to memorize what each equation is, because on the equation sheet, you're going to be given just the equation, just like that, that, and that, and that. But you're not going to be able, but you will not be able to find like the description of the equation. So you have to distinguish between what is the conversion from weight percent to atom percent, and from weight percent to mass per unit volume, right? And then like weight percent, atom percent. So like make sure you're familiar with those equations, okay? In here, we're clearly going to be looking for conversion between weight percent and atom percent. Okay. So between atom percent and weight percent, which is those equations here. Okay, so let's define. So we're looking for the from atom percent to weight. So this is a weight percent. This is C1, C2. Okay, so let's call lead as C1 and this is C2. And our weight percent is going to be C1 prime. So atom percent is going to be C1 prime and C2 prime. Okay, so you just simply use the equation. Okay, and you'll have you'll be given the atomic weights of your atoms. Okay, so in the question you're going to be given that. So atomic weight of lead, bro. Okay, here we go. Lead. Here we go. PB is going to be equal to what's that value? 207.2 grams per mole, and the atomic weight of 10 is equal to 118.71 grams per mole. Okay, so C1 is equal to C1 prime A1, which is just A1, it's A2, divided by C1 prime A1 plus C2 prime A2. Okay, so you just simply plug in the variables into your equation. You don't have to transform 6% to, like, you don't have to divide it by 100. You don't have to, because you do have percentage here. Like if you divide by 100, this will not do anything. So just put like 6 here, put the value of A1 here. C1 prime is, again, 6%, and this is 94%. And you will be able to find that your C1 is going to be equal to 10 weight percent, which is that. And then you can either repeat the same equation by finding the C2, or you can just simply say, since they have two elements, the total weight percent is going to be 100, obviously, right? So your C2 is 100 minus 10, which is 90%. Okay, so you can just only once use this equation. Okay, but if you have more than one element, you have 3 elements, you'll have to modify this equation. So it's going to be like C1 prime times A1 over C1 prime A1 plus C2 prime A2 plus Cn prime En. Okay, and then you will not be able to use this concept of total, right? Because like you have too many variables, right? So yeah, it's quite simple. And all of those equations, they're similar, basically converting from atom percent, weight percent to mass. So what matters is how many elements you have. Okay, on the midterm, you're going to be most likely given 2. If you're given 3, it's also not the end of the life, you know. So simply just use this equation. You're going to be okay. Okay. So do the rest of the questions on your own. And any questions about this chapter? Because I'm going to be moving to the next chapter right now. Just type in the chat yes or no, so I understand we can move on. Ready? Okay, yes. Perfect. Good, fantastic, guys. Thank you. All right, let's move on to chapter 5 now. This chapter should be quick as well. Yeah, it'll be quick. There are questions that were in the midterm. I would like to cover those. And then we're going to move into chapter 9. Hopefully we can finish in 40 minutes. Okay, diffusion. So what is diffusion? Right? So imagine you put 2 different metals, let's say aluminum and magnesium together. Okay, let's assume they're flat. And when you put together both metals, you know, both plates, you have no air between those. Okay, no air. So they're like fully sitting on each other. So each atom is touching each atom of aluminum, touching each atom of magnesium. When does the tutorial end, and will I send the recording to us? Yes, I will. We're gonna have maybe a quick 5-minute break after this chapter before jumping to chapter 9. Or I'm not sure. Do you want guys a break or no? I'm like fine without a break. Just type in the chat Yes break, no break. No break, no break, no break, no break, no, let's keep going. All right, I guess it's just like, I'm fine without a break, so it's okay. I guess just more people don't want to have a break, which is perfect. Okay, cool. We're gonna end in like half an hour or something, okay? Half an hour should be okay. So what was I saying? Yeah, the diffusion. So imagine you have two flat plates, like perfectly flat, and you put aluminum and magnesium plate on each other. There's no air or anything, no liquid and no gas inside between those, I mean. So what's going to happen is after some time passes, you will actually be able to observe that some of the atoms, they start basically migrating into the other plate. Okay, so like magnesium will migrate into aluminum. So atoms of magnesium will migrate into aluminum and then otherwise, okay? It's going to be like some driving force, which is going to be transferring both, atoms into different plates. That's called diffusion. And some like obvious correlations that you might draw. So obviously, if you put two plates together right now, in 1 second, they will not be able to diffuse into each other, right? But with time, you will be able to see that some atoms start diffusing. So time is like one of the most important variables. However, another important variable you also intuitively might feel is temperature, right? So imagine you heat up both plates, like this. So atoms, while the time passes, you can increase the diffusion rate by increasing the temperature. Okay, and as the temperature increases, you will see how there's a more like less time that it takes for atoms to like diffuse into each other. So they start diffusing with the increase of temperature, right? And obviously, if you like melt both things, they like fully diffuse, right? That diffusion also is really dependent on like interstitial and substitutional defects. Okay, but like in this chapter, we're talking about diffusion as an equation and as a driving force. Okay, so let's look into the theory. Hopefully, it makes sense intuitively what a diffusion is. Same happens with the gases, right? When you mix like like oxygen and something else, the gases are more chaotic, so they will start diffusing instantaneously to each other. Right? With metals, with solids, it's a little bit complicated. So we'll have to create some models and equations which are based on those models. Okay. So diffusion is the material transferred by atomic motion. Yeah, so that migration I was talking about of one atom to another, from one plate to another, is called atomic motion. And diffusion is that transport of material by atomic motion. Okay. So interdiffusion, impurity diffusion, they're the same concepts. Make sure you remember those, maybe on the midterm question. Those are atoms of one metal diffused into another. So you have like intradiffusion, pretty much just like one plate inside a plate, like some atoms are diffusing into each other. Self-diffusion, though, is all atoms exchanging positions are of the same type. Okay, so vacancy mechanism only. Can memorize that. For the diffusion mechanism, the following conditions must be met. So there must be conditions in order for diffusion to occur. There must be an empty adjacent site, okay, and must have enough energy to break bonds with its neighbor, lattice distortion, right? That's why you want to like increase temperature to increase like a vibration of the atom so that it breaks from its lattice and goes into the another atom, if there is some space to go, obviously, right? Because if you have a perfect arrangement of atoms on both plates, no, like, and also if the Hume-Rotherham rules are met, then you will not be able to see any diffusion because there is going to be nowhere to go. Even if you start melting those, like increasing temperature, there's going to be no diffusion. Like no space for one atom to go into another plate, pretty much. So a lot of like intricacies into that. So let's look into this red box here, which I emphasized. For the metallic diffusion mechanism, the following conditions must be met. Vacancy, so interchange of an atom from a normal lattice position to an adjacent vacant lattice site or vacancy. Okay, just like remember this. Interstitial diffusion, so it should be small elements like oxygen, carbon, nitrogen, and hydrogen. Okay, remember this, okay? For the interstitial diffusion to occur, those elements must be of a small atomic radius, which is oxygen, carbon, nitrogen, hydrogen. Okay, just as examples. Okay, you might be given like a question in the midterm asking about that. Okay. So interstitial diffusion occurs more often than vacancy. So I've emphasized here, probability of interstitial is much greater than the probability of vacancy. Please remember this, might be a midterm question. So it is most likely that the interstitial diffusion will occur than the vacancy diffusion, okay? Just because of the nature, there are more vacancy locations and more interstitial locations and less vacancy locations, okay? So let's talk about the Fick's first law. So what is this law? This law is defining the diffusion rate, okay? So this law is quite simple. The first law is simple because it allows you to observe the diffusion in one direction. It's a steady diffusion, nothing changes, okay? So it's not dependent on time, okay? You just assume there is a constant rate of diffusion and we call it steady state. Okay, so it's one of the models is to describe the driving force of the diffusion in terms of the steady state model, okay? So basically D is the, I forgot what is D. Is it some coefficient of a driving force? Can somebody remind me what is a D, guys? In the Fick's first law? It's like a driving force coefficient or something. Somebody remembers? No, nobody? That's okay. I'm gonna take a look really quickly. This is chapter 5. The diffusion coefficient. Yeah, okay, perfect. Oh, makes sense. Diffusion coefficient, perfect. So you're gonna be given diffusion coefficient. Perfect, yeah. So this is diffusion coefficient. Diffusion coefficient, perfect. dc over dx is your gradient, okay? So this is your driving force, okay? So this is a so-called concentration gradient. Okay, so as you can see, we have as an example a plate with some thickness, right? And you want to see how the gas at some pressure here, so like let's say a high pressure, there's a pressure difference here. So whenever there's a pressure difference, obviously the pressure goes always from highest to lowest, right? So the gases are forced to diffuse through this metal plate and exit at the other side of the plate. Okay, so because of this pressure difference, atoms are diffusing into the plate. They're like going in some chaotic motion through the metal, then exiting here. Okay, and we want to approximate this, you know, because like whenever the atom enters this diffusion, right, it enters the plate, it will have like to go somewhere here, 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 right, like there, there, and there. So at the end, if you take the mean direction of the vector, it's going to be like this direction. So it's like going this way, okay? So you approximated this model as that, and you say that all oxygen atoms, they like exit in perpendicular, which is like another simplification. They exit in perpendicular to the plate, okay? And we have a given area of the plate, okay? So this is an example of the concentration gradient of the Fick's first law. So if you take a look, the concentration, right, is going to be decreasing with the thickness of the plate. So the more atoms are going to be on the other side, the less atoms are going to be on the right side. It's like a membrane is going to be like filtering some oxygen, and its concentration is going to be decreasing. So only some amount of atoms, only some portion of Ca called Cb is going to be able to leave the plate. Okay, on this side. Yeah, so we also call it a driving force. Okay. So that's simple, just a Fick's first law. Nothing is dependent on time. Okay, but like there is also a second law, Fick's second law, which is like quite more realistic, less like stupid assumptions are made. So you do have something dependent on time. So it's a non-steady diffusion. Okay, so when you have something non-steady, it means that you have something different, some differential equations to work with. You always try to refer to some mathematical tables. Okay, some tables like that. So for this equation, this equation is differential. Okay, this is a differential equation. It has a second order here and first order here, and it is dependent on time. So people did solve this equation, and they came up with the error function. Okay, which basically it's dependent on this parameter, x over 2 square root of dt, okay, which is a constant. Please keep that in mind. It is a constant variable. It is constant, very important. It is constant. Is error function on calculator? I don't know. No, back in my time, like I didn't have a error function on my calculator. You know, if you have, good for you. If not, in the equation sheet, you're going to be given the stable, so you're expected to use the stable. But if you do have error function and if you know how to use it, and please make sure it's going to give you the same values as in your practice question, so that you don't use it like first time in your midterm. Okay, so yeah, I'm going to like teach you manually how to do that. So, but if you have error function, fantastic. Perhaps it's working well. So, okay, so the diffusion coefficient is independent of composition. Also keep that in mind. So whatever composition you have, your diffusion coefficient is static. It's the same. Okay. So a couple of assumptions that are made to solve differential equation above. So basically, based on this set of assumptions, we came up with this equation. Okay, so this differential equation has been solved in this kind of manner, assuming all those assumptions. Okay, so your initial conditions are 0, blah 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 blah. You also assume that your plate is infinite. Okay, your x value is like infinite, pretty much. It's like, yeah, part of the assumption. And yeah, if you're interested, take a look at those assumptions. But this is the solution to the differential equation above. So error function value is stable, and you will need to use interpolations. Okay, you will need to use interpolations. So some value in between here or here, you will need to assume it's linear. You assume it's linear. What else we can do? So yeah, and then you can find the values here between the other values. Okay, we're gonna do one example on that. Don't worry. So yeah, this table is going to be given to you. So if you don't have an error function in your calculator, or you don't know how to use it, it's simple enough to use it manually. Okay. So let's talk about the factors that influence diffusion. I kind of already mentioned that. So it's diffusion species. Well, I didn't mention that. So it's diffusion species influences the coefficient of V. So the material that you have, okay, has its own diffusion coefficient. Okay, they have been experimentally defined. You have for each metal, aluminum, magnesium, blah, 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 blah. You have each element, you have diffusion coefficient. And obviously, temperature and time. Those are three main factors. So element, time, and temperature. Might be a question in the midterm. What are the factors that influence diffusion? So A, B, C, D, you must pick the one which has diffusion species or elements, temperature, and time. Three factors. Keep that in mind. Okay, three factors. Okay. So this question, which is quite similar to the activation energy question from chapter 4, which is a little bit different still. This allows you to calculate your diffusion coefficient. So D0 is always constant. It's like Boltzmann constant, like Avogadro's constant is always constant. And your QD and temperature, okay, those that are, you can experimentally determine for some metal, your coefficient, diffusion coefficient, pretty much. We're going to use this in an example. We're going to be given D0, QD, and temperature. I mean, this is just like one question, plug and play, okay? Nothing much. Yeah, this is the expanded version of that, in case you're looking for something else. Okay. We're done with the theory portion of it. Again, I would encourage you to read the chapter yet. So again, let's work on the practice problems, right? So this is chapter 5 for me. Okay, cool. Let me see which questions were in the midterm last year. We can practice those. Okay, so question 3 was in the midterm. Yeah, similar question was there. Tricky question, but kind of good question. So we're going to do one question that involves the use of the table. Yeah, that's going to be question 2 and question 3. Okay. All right. So let's read the question. Okay, determine the carbon rising time necessary to achieve a carbon concentration of 0.45 weight % at a position 2 millimeters into an iron carbon alloy that initially contains 0.2 weight% of carbon. The surface concentration is to be maintained at 1.3 weight% carbon, and the treatment is to be conducted at 1000 degrees Celsius. Use the diffusion data for the iron in table 5.2. Okay, so a lot of information. Okay, so what we have to, okay, let's understand what we're looking for. We're looking for a time. Okay, we're looking for some time. We're given an equation which allows us to relate the diffusion rate, so let me scroll up, the so-called concentration gradient driving force to time. And obviously, if you're asked about time, it has to be fixed second law. Okay, so it has to be fixed second law, because if you don't have any time involved, it's going to be fixed first law. So it's a steady state. So that's the first thing you have to catch and understand, right? Because the first question, when you're going to be working on your own, is going to be it's not going to involve any time. Okay, so you're going to understand no time. It's going to be fixed first law. Here we're looking for the time, so we know that we are going to have this differential equation that we're going to have to solve. It's already solved for us, so we'll have to find time. So given, let's find out what is given. Let's write down the equation first of the fixed second law. Okay, so this is the equation. This is the solution. There's no need for writing this down because it's just a differential equation. The solution is this. So Cx minus C0 divided by Cs minus C0 is equal to 1 minus error function x divided by 2 root of gt. Okay. Okay, so now we have to understand what is Cx, what is Cs, and what is C0. What is x and what is d? Okay, because obviously from here you will have to use that table that I described before, right? In order to find this coefficient. This coefficient, right? From which, after you obtain its value, let's call this value b, you will be able to find your time, right? By just simply isolating in for t. So the most complicated part is not to get lost in the definitions of Cx, Cs, and C0. Okay, so let's read the question again. So we want to achieve a carbon concentration of 0.45 weight% at a position 2 millimeters. Okay, so if you were to take a look at the plate, let's say plate has some length L, and it has some distance x in which we're interested. So that's the distance x, which is in our case equal to 2 millimeters, right? So at this distance, we want to have our concentration value to be 0.45 weight%. Okay, so at this distance, so let's read it again. Determine the time it takes to achieve a carbon concentration of 0.45 weight% at the position 2 millimeters into an iron carbon alloy. So this is an iron carbon alloy. Okay, iron carbon alloy plate. We're passing some carbon through it. Okay, and we want to observe the time it takes for the carbon to have a concentration of 0.45 weight% at a distance of 2 millimeters away from the surface, from the start surface. Okay, so from the surface pretty much. As it enters here, after 2 millimeters of migration of the atom, you want to observe this concentration of 0.45 weight%. So then you need to calculate time. Also, you know that initially, your into an iron carbon that initially contains 0.2 weight% of carbon. So initially, this metal plate already has some amount of atom, okay, of the carbon. So that's going to be 0.2 weight%. So initially, so you're given Cx, which you want to find. So this is the location of the interest, okay, so which is 0.45 weight%. So this is where you want to have 0.45 weight%, which is 2 millimeters away from the entering surface. You're given the initial concentration of carbon, which is C0, So 0 like initial, kind of intuitive, 0.2 weight percent. Okay, and you also have the surface concentration. You want the surface concentration to be maintained. So S is denoted for surface concentration, okay? Surface concentration. So you can write down that CS is equal to 1.3 weight percent. Okay, so you're pretty much given all of the stuff. You can just go ahead and plug it in. So CX is 0.45 minus 0.2 divided by 1.3 minus 0.2. Okay, that's going to give you 0.2273. Okay, and that is equal to 1 minus ERF of B. Okay, so I call B as X divided by 2 root of dt, just for simplicity. Okay, so 1 minus ERF of B. So when you isolate for ERF of B, okay, that's going to be 1 minus 0.2273, which is going to be equal to 0.7727. Okay, so your error function you found to be 0.7727. What you're interested in, actually in the table, they defined it as not as B, but Z. Sorry, let's be consistent in terms of variables. Z, that is also Z. Okay, and this is also Z. Oh, here we go, Z. So you have error function of Z, which is a Y value. You want to find whatever is inside that. So the dependent variable X, which is Z in our case, right? So in order to do that, you have to go to the table, right? So this is your table. So this allows you to extract your X value out of your Y value. It's like a simple function, Y is equal f of X, okay? Similar, this is your Y, this is f of X. But here f is your error function, okay? So you will have to use the linear interpolation in order to do so. So let's go take a look. We have 0.7727, right? Like obviously we will not have exactly this value, right? So like, yeah, the closest value that we have is 0.7707. Okay, so 7727 lies between this and this variable. Okay, sorry, not variables, between these numbers. Okay, so what you have to do is you have to take out these two numbers. Okay, Z, and you're given ERF of Z. So let's rewrite it. Let's rewrite it here. So our Z, our ERF of Z, so this was 0.85. This is Z we're looking for. So this is like variable. Okay. And then 0.9. 0.7707, 0.7727, and 0.7970. So 727 is what we found. 70, this is from table, this is from table, from table, from table. This is what we're looking for. Okay, then hopefully you remember how to do your linear interpolation from your high school, guys. Okay, so that, so you can relate this. Yeah, you assume everything is linear here. Okay, which is like fine, whatever. So in order to do the linear interpolation, you write it down this way. So Z minus 0.85 divided by basically the difference between this and this one divided by the difference between the outer ones, minus 0.85 is equal to a symmetrically same. So 0.7727 minus 0.7707 divided by 0.9, no, sorry, not 0.7970. Do you know if the RF value table will be included? Yeah, it will be included in the formula sheet. It has to be, you cannot just memorize it, right? So that's going to be in your formula sheet, minus 0.7707. Okay, so after you calculate all of that, your Z value, jeez, what happened? Oh, did it just get removed or what? Oh my God. What happened here? Okay, something happened here. But anyway, after you construct your table, okay, guys, you have your linear interpolation. Bruh, what happened here? The linear interpolation. So when you calculate that from that fraction that I had, okay, you will get your Z value to be 0.854. Okay, make sure you practice it before your midterm. Write down those values, value, what you're looking for, and value. Okay, so you'll get your z as 0.84. From here, this is going to be equal to x over 2 root of dt. Okay, so and also so it does ask to find the diffusion data and go to the table 5.2. If you actually go to this table, you will be able to find that at 1,000 degrees of Celsius, your diffusion coefficient is going to be d. So you're going to be able to extract it from your table. Okay, so 1.93 times 10 to the power of -11 meters squared per second. Okay, so that's the diffusion coefficient you'll be able to find from the table. Obviously, in your midterm, you're going to be either given it or you will be able to find it using the equation here. Okay, so they're going to give you like D0, QD, and temperature. Okay, like here we couldn't solve for it because I wasn't given QD, right? So, but we have temperature. So yeah, this question is like just relied on the table. Anyway, if you go on the table, you'll be able to extract this info. Okay, and that's pretty much it. Yeah, so you have your Z, you have your X, you have your D. X is equal to 2 millimeters. Okay, and you will have to, it will be given, yeah, it will be given, diffusion coefficient. And if it's not given, again, you'll be given something like that. So you'll be able to find your D anyway. Again, it's just like plug and play numbers, nothing much. Yeah, make sure you transfer from millimeters, go to meters for sure. Like, yeah, don't make this mistake. Yep.
What's the units for D?
Units of D?
Yeah.
Meter square per second. Sorry, let me.
Thank you.
Meter square per second. Yeah, it
And
has
this
to be
question
meter
was
square per
asking
second.
for time, right?
Yeah, it was asking for time. So you isolate for that, right, from your Z value. So quite simple, right? So you'll put your X, since X is like the location at which you're interested, right? The time it takes to get into this location, which is 2 millimeters, which you have to transfer into meters, okay? And then you're given your D, you have numbers 2, right, and T, right? So after you isolate for your T, right, so let's square all of that. It's going to be Z squared is equal to X squared 4 dt. So T is simply X squared divided by 4D Z squared. That's your final equation. You plug in your values, you're given Z, you're given X, convert to meters, make sure meters. D is given as meters per second, meter squared per second, because this is in meters, right? It has to be in meters as well. It has to be in meters as well. This has to be in meters. So yeah, so after you calculate all the stuff, you'll be able to determine that the time it takes to diffuse the carbon at 2 millimeters to a certain concentration based on the initial parameters is going to be 19.7 hours. Okay. Kind of, I don't know, makes sense. Just like after you do some questions, like make sure you like think about the answer you got. So that if you're like got some ridiculous value of 2 seconds, it's kind of ridiculous, right? You cannot just go for 2 seconds. Like for gases, yes, it's possible. For solids, it's going to take a lot of time, even at high temperatures, like 1,000 degrees Celsius. Okay, that's iron, so that's kind of expected, right? Iron, melting temperature of iron is called austenite, as far as I remember, like this gamma sign, but whatever. Melting temperature is high, so do we keep the answers in hours because the D is in seconds? Okay, you will get. Okay, yeah, of course, you will get seconds as your value. Like it depends what is your ABCD, right? So if your ABCD has hours as your unit, convert it to hours. Might be even days, so make sure you know like your conversions, right? Should be simple. Okay. Any questions on that? Any concerns? Any comments? I guess no, right? Okay. Let's move on to the question that was in the midterm. Similar question. Okay. In this study hall, content available in D2L. Okay, so no, it will not be available in D12. I will post it on my website. I guess it's time to post my website again. You'll be able to find the Dropbox link there, as well as the recording to this presentation, which I'm going to put on the YouTube. Okay, so you will be able to access it only by a link. So my name, my family name, enko.com. Here we go. That's my website. Pretty sure the last part again from the question. Okay, wait. So Ryan asked first. So temperature doesn't affect the calculations. What do you mean? The temperature is constant here, 1,000 degrees, right? So it's constant. So like you get your answer. But if you had different temperature, the time would be different. If you have larger temperature, your time will decrease. Okay, if you have smaller temperature, your time will increase. The temperature is okay. Just like memorize that. This is important. Okay, but here temperature was constant, so you know. Did you understand what I mean, Ryan? You know, like, does it answer your question? Like temperature does affect the calculations, but in this question, temperature is constant, so it will not affect anything else. I mean, do you get it? Just shoot the answer in the chat. So, could you show the last part again from the last question? From the question solution, sure. Yeah, I can. So yeah, okay, Ryan. Yes, thank you. No problem. So, the things I was working on here got deleted. Sorry about that. I don't know what happened. But I'm gonna be posting solutions. They explain it also well enough that you have to construct the table here. Use the linear interpolation to find your z. From z, you will be able to you equates that to your value of x over root of dt. Yeah, okay, so should be understandable. From there, you just isolate for t, and that's it. Okay, let's do the last question from this just this chapter. Okay, so that's the question about diffusion as well. So for a steel alloy, it has been determined that a carburizing heat treatment of 10 hours duration will raise the carbon concentration to 0.45 weight% at a point of 2.5 millimeters from the surface, from the entering surface, right? Just like visualize whatever we have here, right? The carbon enters into the plate and blah, 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 okay? So estimate the time necessary to achieve the same concentration at a 5.0 millimeter position for an identical steel and at the same carburizing temperature. Okay, so what you might do first is just like put in the equation of your fixed second law, right? And then you will be able to understand that you're not given enough variables, and you will be lost. Okay, so the trick in this question is actually in the last sentence. It says estimate the time necessary, blah blah blah, for an identical steel and at the same temperature. So you have the same material and you have the same temperature. Okay, so I emphasized beforehand here that the x over 2 root dt is constant. It is constant if your temperature and your material are constant. Okay, so it's going to be the same for the same material under the same temperature. Okay, and like, I mean, even if the temperature is different, yeah, no, temperature has to be the same and the material has to be the same. Yeah, so only then this value is going to be, it's like two conditions: first condition, second condition, and you're going to equate both. And from this simple ratio, you'll be able to find your time. So let me show you if you don't understand that. So let's write down what is a given. So we're given that T1 is equal to 10 hours. We'll raise the carbon concentration to, so let's say just the concentration is equal to 0.45 weight% at a point of x1 is equal to
Sir,
2.5 millimeters. Yep, sure.
Is this raising concentration? Is that the CX?
In this question, it kind of doesn't matter. I'm gonna show you what that is. Okay, so it's just like yeah. Let me explain what that is. I'm gonna like show you. It's just like a concentration that you have, right? So look, it says same concentration, right? So you don't care whether it's CX, CS, like it's going to be CX, obviously, because you're looking at a specific location at which the
Right.
concentration is going to be, right? But in this question, like you don't have to put CX. Like,
Okay.
yeah, conceptually it is a CX,
Okay. All right.
but
thank you.
yeah, just 0.45 weight percent. Yeah. Yeah. So basically, this problem. Okay, let me write down what is given. I'm going to explain what is going on. So in the first condition, we had at a certain temperature in a certain material, we observed that it took 10 hours to get into 2.5 millimeter location, and we observed the concentration of 0.45 weight percent. Yeah, so yeah, it's CX pretty much, yeah, but CX here at 2.5 millimeters was 0.45 weight percent. And it took 10 hours to achieve that concentration at that distance, okay? So we want to estimate the time. So we want to find T2 now to achieve the same concentration. So we want to understand, we want to find the time it's going to take to reach the same concentration, okay? If the material were to travel twice the distance to 5 millimeters, okay, to 5.0 millimeters. Okay. So the trick here again is to understand that you're working like with identical material and an identical temperature. So you're traveling first of all here at 10 hours. In 10 hours, you determine that at 2.5 millimeters, you observe 0.58%. But let's say you don't want to repeat this experiment, but you have equations that you derived, right? And now you want to infer, you want to extrapolate the data, and you want to say that what happens if I double my distance and I keep my concentration the same, and I keep my material the same, and I keep my temperature the same, right? So you want to find what amount of time it will take for that same parameters, to get me to the same concentration. Pretty much, that's the whole point of the question, right? So the trick here again is to understand that your Z value, which is x over d root of dt, is the same, it's constant for the same material and temperature, right? So it means that your x squared over 2 root of dt is constant. Okay, and yeah, so
Sir,
yeah,
question. So for that to be constant, the x squared, it has to be same temperature and same material.
yes, it has to be the same temperature, same material, yeah, and same concentration as well. So like it has to be like super identical in that kind of matter. Okay, make sense? Okay, I suppose it does. All right, cool. All right, let me see what's going on here. Blah, blah, blah. Square the team. Okay, let's see what happens here. So that is the same. So we say that x1 square over d of, or square root of dt1 is equal to x2 square over 2 root of d dt2. Okay, so 2 cancels out. We have x1 squared divided by root of t1 is equal to x2 squared of root of t2. Okay. The solution manual says that, guys, look, x squared over dt is constant. It drops out the square root for some reason. That's what the solution manual says. I'm not entirely sure why. Maybe somebody has a clue, but in the solution manual it says that this has to be maintained constant. So they drop this.
They squared everything, the constant.
You do square it, but it's already squared, right? Isn't it? In the equation.
It's not. I don't
Oh,
think it is.
it's not. Oh, sorry, guys. I just got confused. I was looking at this and I was looking at the solution manual. I squared this, but I didn't square that. Now it makes sense. Perfect. Thank you. Yeah, sorry about that. But it makes sense now. So sorry, I squared like right after that. So okay, no confusion now. You just write down that constant, that value is indeed constant. Okay, so what you do is you have that simply, and now it all should make sense. Perfect. Sorry, I just got confused by looking at two different things. Awesome. Perfect. We can erase that. So this is the final equation that we have. Okay, x1 over root of t1 is equal to x2 over root of t2. And if you indeed square that, you will see the same as what solution manual says over t2. So that's identical to that. And you're given x1, you're given x2, you can find t1 and you can find t2, right? You don't, as I said, you kind of don't care about the concentration here because it's going to be the same anyway. So x1, and you don't need to change your units, right? Because it's just ratios. So you have 2.5 squared over 10 hours is equal to 5 squared over t2. So t2 is simply 10 multiplied by 5 squared divided by 2.5 squared. That's going to be equal to 40 hours. Okay, so it means that if you increase the distance by a factor of 2, your time will increase by the factor of 4 because you square your distance. So time change is proportional to the distance square change. Okay, just interesting fact out of it. Yeah, so during your midterm, if you have this question, then you will just you will not need to do this division. You'll just be able to see that if you square your distance, your time will be if you increase your distance by a factor of 2, you square that distance change. Okay, and you'll get your time. Okay, so 10 hours, 40 hours, kind of makes sense. Okay, so any questions on that? Sorry, could you explain why I didn't hear you? Could I explain what? Sorry, I wasn't keeping an eye on the chat. Never mind. I got okay, perfect, awesome. Any other questions that you have? No. Okay, I assume no. All right, let's jump into the last chapter. Okay, so this is chapter about. Can you repeat y we square x? So you do not. I made a mistake. You don't square x right beforehand. You just write down that this z variable is constant. So you equate. So you have your z1 is equal to z2. So your x over 2 root of dt is equal to to that. Okay. So and then you cancel out all the like terms because they're the same, and then you end up being with this value, with this equation, and then you square all of that. Okay, and you will get the same value here, same equation. Okay, so you square it to get rid of the root, pretty much. Okay, but yeah, don't put square here right after I just made a mistake here. Like that. Okay, but that makes sense. Okay, let's jump into chapter 9 right now, phase diagram. So what is a phase diagram? So in your high school, you might recall that you were looking into like unary phase diagram, which is like a physical state of your water. So you know that your water can be liquid, can be ice, can be gas, right? So you were looking at how pressure and temperature are related, right? So as you increase that pressure, as you increase temperature, you observed how the physical state of your water changed, right? And this is like a simple diagram summary. Like at this kind of pressure, right? As you increase temperature, right? Let's say to 80, and as you increase, like let's say at standard sea level conditions, if you increase temperature to 80 degrees, your water will still be liquid. But if you increase to 100, it will boil and it will become gas, obviously, right? So yeah, that's like one of the examples of this simple phase diagram, a so-called unary phase diagram. So that's for gases and liquids, right? So for solids, for metals, we also have phase diagrams, okay? Those phase diagrams allow us to determine a specific composition, right? So if you have aluminum, aluminum and let's say carbon alloy, right? Let's say you have aluminum 80%, 20% carbon, right? By looking at the phase diagram, you can determine at what temperature if you increase the temperature, this specific composition will be in a solid state, will be in liquid state, semi-solid, or liquid state, or even gaseous state. Okay, but like you never want to like evaporate your molten alloy, right? So you want to be in a liquid region in order to melt it, right? So that's the main complexity of the chapter, is that your phase diagram is just simply a composition versus temperature, right? And you do have different interesting regions that we're going to be looking into. So it's all about what composition of metal you have, and with the increase of temperature, how will the composition behave? How will the alloy behave as the temperature increases? So we're going to observe that. Simple water phase diagram contains triple and invariant points, right? So this is a triple point as far as I remember. Anyway, so externally controllable parameters, you can control pressure, temperature, and weight percent. Okay, quite simple. So you have binary now isomorphous systems. Okay, so we're closely approaching the so-called binary eutectic systems. Okay, so here let's observe what is a binary isomorphous system. So this is a relation between the temperature and weight percent. So in this kind of, how is it different from the binary eutectic system, is that it only has this region, it's isomorphous. Okay, it only like has this kind of interesting region between the solid, liquid, and the solid, semi-solid, and liquid. So we call this region semi-solid. Okay. So when you actually start casting your metal, you will be passing this point, right? If you keep your temperature, if you keep your composition constant, which is the case, right? You just increase your temperature. So from solid, you will be able to observe, so a portion of liquid and solid, right? It's called, like I call it, when I melt metal, I will be able to observe this slushy region. I call it slushy region because it's kind of weird. It's like slushy, it's liquid and solid. It's kind of cool to observe, but you pass this point, and as soon as the more temperature increase, the more you will see liquid. And at some point it will surpass the liquidus line, so-called liquidus line, and everything is going to melt. And you will be in the melting region, in the liquid region, okay? And everything beyond that, it will be quite dangerous for your metal, as it will be catching more oxygen. And well, that's another topic. But at some point you will evaporate your atoms, so they would just fly from the crucible, pretty much. But you don't want to do that. So, right. So for aluminum, the melting temperature is 700, about 600. Aluminum, silicon, copper, 700 degrees Celsius, right? So as you increase, let's say for aluminum, right, you will be able to pass that region and go here. But that'll be a different topic about the binary eutectic system. For the binary isomorphous system, an example for that is going to be the copper nickel alloy. Okay, so that's the example of the binary isomorphous system. Right, so and here we're going to be talking about the lever rule, okay, the tie line, and calculating the portion of your liquidus, portion of your solidus, of solid and liquid inside your metal, right? As you start, increasing the temperature. At a certain temperature, you want to stop and observe what kind of ratio you have. Was it 60 to 40? No, like it will depend like at the location of your composition at the temperature. It's not like constant everywhere. Yeah, so like it does depend. Okay, on the composition and the temperature. So there are procedures how to draw tie lines on the isomorphous binary systems. Okay. Please go over those procedures. Okay, on your own. Also, you will have to practice it. I will quickly show you because we're running short on time. Let's wrap it up quickly. Those equations allow you to calculate in your isomorphous systems. They allow you to calculate the amount of liquid, amount of alpha base. It's called alpha homogeneous liquid solution. Yeah, so it's like amount of portion of a solid that you have inside your metal. So again, if you're in this region, right, you're in this region, you will have liquid and you will have solid. The whole purpose of the timeline is to calculate how much of a portion of a solid and liquid you have. Overall, you have 100, right? So you will have to calculate portion of solid, portion of liquid at this specific location at this composition. So we're going to do practice question of that. C0 will be given, or we have to find it. C0, you're going to be given that. Yeah, you're going to be given that. We're gonna do a practice question. You're going to see. Blah blah blah. Yeah, look into phase volume fractions. This is like a chapter in your textbook. Not likely going to be asked on the midterm, but just still like make sure you read that here, like you have it in your memory. So microstructure development in isomorphous alloys. So there's one term that you want to be familiar with, which is so-called equilibrium cooling. Flow cooling till equilibrium. So basically the reason for it to be used is the diffusional processes, which are time dependent. So you want to have a steady system. It's like one of the assumptions that we model in this kind of chapter is you have a steady system. So you like temperature increase is constant, your time is like irrelevant. You just like observe your system. Less variables to play with, much. Yeah, and like this diagram kind of interestingly depicts how the copper will behave in nickel, or how nickel will behave in copper as the temperature increases, right? So at first you have your fully solid state, then you start increasing, right? And you start like segregating, like for forming pretty much like small portions of your solid while getting the liquid already like somewhere in between, right? As you increase the temperature, you'll get more liquid, right? As you get more temperature. So here, this region, it's called the solidus line. At the solidus line, this is the point at which you'll start forming some liquid around your portions of your solid. Would that line be given in a diagram, or would we have? You have to draw it yourself. Yeah, you have to draw it yourself, and I'm going to show you how. So as you start increasing the temperature, you will form more and more liquid, which is quite obvious, right? You form more liquid, you form less solid, and at some point you get a liquidus line. So you also have to be familiar with the names of lines. This is liquidus because it's touching the liquid and the semi-solid region. You have solidus line because it's touching the solid and semi-solid region. So on the bottom, you always have solidus line, top liquidus, okay? This is a so-called semi-solid region, okay? So obviously at the liquidus line, you will have the least amount of solid present, but still you're kind of like, in the semi-solid region there. But as soon as you surpass that point, you're going to get fully to liquid region. Cool, perfect. That should make sense. So non-equilibrium cooling is crazy. It's pretty much unsteady, unpredictable. You start like coring. Coring is when you have formation of like layers of your atoms like forming on another layer. Kind of gets crazy. It's when your equilibrium cooling is not even, or yeah. So from here you have to understand that just like you have coring pretty much. Okay? If you have non-equilibrium cooling, you will have coring. Coring is when you have your atoms, they start growing by layers and layers and layers and layers. Okay. So usually when you pour your metal inside a mold, right? So you pour your metal inside a mold, right? Your mold will have a temperature difference between your molten alloy, your red, and the mold. So usually you want to preheat your mold. So let's say aluminum would be at 700 degrees Celsius. Your mold will be like at 400. So that temperature differential 300 Celsius, right? Sorry, is the solidus line on the bottom? Yes, the solidus line is on the bottom. Because of this temperature differential, the atoms that are touching the walls of your mold, they will quickly start cooling down, which gives you the non-equilibrium cooling. So they will start like coring pretty much, which is like not really good when you start for your metal, like for your part, for your sample, you don't want to have like coring that occurs. It kind of like gives you like really bad mechanical properties. So that's another topic of discussion, yeah. But in the middle of the metal, which is in the mold, you'll be observing actually equilibrium cooling. So it'll be relatively stable, right? So that's why when you like start observing the microstructure of your metal, when you start cutting your metal, grinding, polishing, then take a look under the microscope, you'll be able to observe different properties at the edges of the walls and at the center, right? But if you do everything correctly, like it's not big of a deal, honestly. So yeah. But if your mold is at room temperature, 25 degrees, and you pour into 700 Celsius degrees, like, bro, that's gonna be like bad. So, and especially if it's let's say like some titanium at 1800 Celsius, it gets crazy and you will start forming the scoring pretty much. Yeah, there's more into it. So there's a lot of thermodynamics, a lot of interesting stuff that happens. So in a basic course like this, you just have to understand that if you have something non-equilibrium cooling, if the temperature differential is really large, you will start forming layers of your atoms, start growing. Yeah. So binary eutectic systems. Let's jump to binary eutectic systems. Binary eutectic systems are quite interesting. And so as an example, we're going to do right now is copper silver. This is one of the examples of the binary eutectic system. Quite large. You have a lot of stuff, more than in the isomorphous systems. Okay, so you have solid region for both. You have, for this composition, the smaller it is, right, you do have a solid region only for solid region only for alpha, only for copper, silver. Then you have for silver only solid region. You can have a little slushy, you know, semi-solid region for copper only plus liquid, silver plus liquid, and then as you pass this region, you will get into liquid here. Okay, so one of the most interesting points is so-called eutectic location. Eutectic location, if you have a eutectic composition, which is 71.9, so it means you have 71.9 of copper and the rest of it is silver, then if you start melting this down, you will not actually get into semi-solid region. So you will not be able to observe any slushy things, you know, inside your crucible. Quite interesting phenomena. You will just be able to like jump right into your liquid. So at some point it will just like change its physical state into liquid. Just like interesting phenomena. Now let's observe the names of lines. So as from before, this is liquidus, this is solidus line, liquidus solidus. This is also solidus line, this is solidus. This is solvus line. Solvus is between two solids. So 71.9% is copper. Yes. 71.9% is copper.
Sir,
Okay. Yep.
is that middle straight line the eutectic system line or eutectic line? Or
This
no?
is, yes, this is a eutectic line. Yeah, but you right, this is a eutectic line. Oh shit, did I call this solidus line?
Yeah.
I think I did. Yeah. Okay. Sorry. My bad. No. This is solidus line. This is a eutectic line. Okay. This is solidus. This is liquidus. This is solvus. Solvus line is between two solids. Okay. So eutectic line for binary eutectic systems is going to be between your semi-solid region and solid region. Okay. And your solidus line will be between the solid and the semi-solid. Okay. And your liquidus, as it was in isomorphous systems. Okay. Yeah. This is called eutectic. Yeah, thank you for pointing this out. Eutectic line. Very important line, eutectic line. Cool. Okay, so solvus line separates alpha solid phase from an alpha plus beta solid phase. Yeah, solvus line, as I said, separates two solids. Okay. Solidus line separates the alpha and alpha plus liquid phase. So solidus separates solid from slushy semi-solid region. And this is like a eutectic reaction. So cooling, heating, like you just pass from liquid directly into solid. That's what it says. You pass from liquid to solid region, alpha plus beta. Okay, so in eutectic systems, you'll have different physical, interactions between your two solids. So depending on the composition, you will start forming primary alpha, primary beta, eutectic alpha, eutectic beta phases. Okay. It gets complicated. What you have to just understand is you have one composition, you have temperature line, right? As you like start decreasing or increasing, doesn't matter. Let's go from here. You go from liquid, you start forming some alpha phases. Okay, if you're in this region, if you're in this composition, you will start forming first when you go from liquid a copper small structures. Okay, then as you go down more, you will see how like the copper atoms, they start growing and growing and growing. And at some point, as you pass the eutectic line, you will start growing some kind of like this pattern. Like this pattern is not actually like true how it works. If you were to observe this under a microscope, it like really depends. I've never seen copper and oh, it's lead tin. Yeah, I've never seen lead tin under the microscope, so like I cannot definitely confirm that. But like theoretically, that's how it should look like. You start forming in the liquid region because you see like this copper, it stopped growing here. It started creating some sort of like lines here. Right? So your primary alpha is your copper, but then your beta is going to be like, so your tin, right? Yeah, your tin is going to be like forming some weird lines, right? Yeah, and the interaction between the alpha beta structure is called grain boundaries, okay? All of this black is your grain boundaries. Okay. So grain boundaries is like your crystal structures, right? They start interfering with each other. The mismatch between how they stack with each other, like it's not going to be perfect. They will form some like inconsistencies, right? And as they start stacking, it's called fold stacking, stack and fold. Okay, they will form some like boundary, and you'll be able to see it on your sample if you like polish it. You're going to see those boundaries. Basically, it's interface between two different phases, two different structures. Okay, that's quite interesting. Yeah. So that's said about it. Also, yeah. So the main equations that are used for eutectic phase calculations, yeah, it's gonna be a little bit more complicated because you have eutectic now. It's one more variable to play with. So you have alpha phase, eutectic weight percent equations, beta phase, alpha phase again, and basically a different relationship between both. So you will need to construct Lever rule again, right? If you're in this region, you will be able to use these values. So you're going to be given composition. You will need to find some, some weight percent of some phases, some structures. So phase formations, please make sure you know of this one below, blah, blah, blah. Yeah, you have to know the location of eutectic, eutectoid, peritectic, congruent, and monotectic points. Okay, so this is eutectic point. This is eutectic point. Eutectoid, I don't remember, guys, honestly. I don't remember. Take a look at the textbook. Make sure you know the location of each point. Peritectic, eutectoid, congruent, and monotectic. Would these calculation questions be more of a short answer compared to the multiple choice? I don't think you have like short answer. I think your midterm is going to be all multiple choice. Okay, so I'm not sure if it's getting changed this year. I don't know, but like if you have some short answer questions, yeah, might be some short answer questions. Again, be prepared for everything, right? This document is a good summary of everything. So, yeah, sorry, like I don't know. I'm not teaching for this course this year, so I don't know what's going to be for the midterm. Exactly the format. What I can say is that last year it was fully multiple choice questions. There's no short answer. So, yeah. Okay, let's talk about the Gibbs phase rule. How is the marking scheme again for the multiple choice? I believe it's so the multiple choice that just a theory question. Sorry, it was one mark, but then the calculation questions, which were also multiple choice questions, they were 3 or 4 marks, or like 2 marks, something like that. Yeah, it's gonna weigh differently compared to the theoretical question. Yeah, that was last year. I mean, yeah, last year midterm. We had like 5 or 4 calculation questions last semester for the midterm. Yeah. Anyway, let's talk about Gibbs phase rule. Very simple rule. Basically, it allows you to calculate the amount of degrees of freedoms that you have in your system. Degrees of freedom says like you have parameters that you're trying to vary, like pressure, temperature, composition, and blah blah blah, right? So the Gibbs phase rule allows you to determine the degrees of freedom pretty much. So P is the number of phases that you have. F is the number of degrees of freedom, so external variables. So basically Gibbs phase rule is always used to calculate the F value, the amount of degrees of freedom. So how many parameters you can vary to satisfy the conditions of your experiment, pretty much. C is the number of components. So in eutectoid and the eutectic composition, sorry, in eutectic tables, you will have only two, right? Two elements. And by the way, like 2 elements is like not maximum. You can actually have 3 elements, and those phase diagrams, they go 3-dimensional. And they're crazy. Like if somebody's interested, look up like after the study hall, like 3-dimensional phase diagram, it just gets insanely crazy there. For super alloys, you might have like 4 or 5 elements, and it crazy gets there. Yeah, so in this course, only 2 elements. Right, so C is going to be either 1 or 2, right? If you have like a water, it's going to be just 1. If you have isomorphous or eutectic structures, it's going to be a 2. So N is number of non-compositional variables. I'm going to have an example of that. I'm going to explain what N is, okay? Okay, since we're running short on time, let's do one example for that and one example for the Gibbs free rule, okay? I think it's that, yeah. So let's do one example for the tie line, okay? So, okay,
So I got a question, quick question.
yeah.
Let's scroll up to the phase transformations and go to like paratectic, congruent, and monotectic. What are these exactly?
Oh man, I don't remember honestly. Like I'm gonna be honest. Like I don't remember what.
These are like the graphs that you're
So
showing.
right, eutectic. Basically, those are the points on your graph. Okay, and here we have eutectic for sure. This is a eutectic point. Okay, this point has also a name. I don't remember honestly what the name is.
Okay, that makes sense now.
So the textbook, yeah. So those points, the intersection points, I may call it. So those are going to be, those are going to have names. Okay.
Oh, okay.
Just take a look at the textbook. I'm sorry, I don't remember that. Like people don't use it often. And yeah, like eutectic is what I remember from MTL200. So those are called something peritectic, eutectoid, congruent, monotectic. Yeah, just take a look at the textbook because there are some phase diagrams that are crazy. I think I have one here. Yeah, exactly, right here. So that's the tin versus magnesium eutectoid diagram. So you see how many points are here? It just gets crazy here. So at each point will have like a different name. So there's going to be some, definitely going to be some congruent, peritectic, eutectoid points. Right. Just like know this. I just saw the 3D phase diagram. That's, yeah, that is mine. Like, that's crazy. That is indeed. Yeah, okay, so it was private. Yeah, somebody like looked up the 3-dimensional phase diagram and just was scared. Yeah, it's definitely scary. Anyway, let's do question number 1. So a 90 weight percent of silver and 10 weight percent of copper alloy is heated to temperature within the beta plus liquid phase region. If the composition of the liquid phase is 85 weight percent, determine the temperature, composition of the beta phase, and the mass fraction of both phases. Good example that can be on the midterm. So let's write down what is given. Okay, so we're given that we're given a 90 weight percent of, oh shit, 90 weight, god damn it, 90 weight percent of silver and 10% of copper. So that is the graph usually given to, yes, yeah, of course, like if it's not given, you know, you're not going to be able to do anything. Right, so 90% copper, silver, 10% copper. Is that what you're saying? Yeah. So okay, here we have copper going from the left. No, so we have composition of weight percent of silver. So all of that is a silver pretty much. Okay. So what we're interested in is 90% of weight percent of copper. Is that? And 10% of copper, right? So this is 90% of silver. Obviously, we're going to have the rest of 10% of copper. Here we have like silver. Here we have pure copper, pure silver. So this is an alloy. Going from 0 to 100 will give us an alloy, not including 0 to 100. Okay, so basically what you're doing is that. Okay, I don't have a straight line feature here, but that should be good. So as we start increasing temperature, we're going to be going in this line, right? So alloy is heated to temperature within the beta plus liquid phase. So we know that we're going to be somewhere in this region, somewhere in this region. That's what it says. if the composition of the liquid is 85 weight%, weight% of silver. Oh wait, what? Liquid phase is silver. Sorry, give me a second, guys. 85% of silver. Yeah, sorry, it's not W. It's gonna be C actually. So here we go. Yeah. So C of liquid is going to be 85 weight%. Basically, what it says that 85 weight% here is that point. Okay, that's the liquid. Okay, so whenever you see liquid phase, it means that it's touching the liquidus line, and at 85 weight%, that's going to be that. Then you start drawing your tie line, which is perpendicular to your temperature line. Right, so you're going to form this line. So what it is asking us is to determine the temperature of the alloy. So just by doing that on the diagram, we can already determine the temperature. The temperature is going to be about like 820 degrees or something. It says 850 on the solution manual. Like, yeah, about there. Question?
Yeah. Why are we drawing these horizontal lines? Is this just to determine temperature, or is it like?
Yeah, in order to determine temperature as well as the composition of your. So the second part is composition of your beta phase. Okay, so composition of your copper inside your alloy at that temperature. Makes sense, yeah. So this is the amount of liquid that we have, okay, because it's in liquidus line. When you go to solidus line, right, you determine your beta composition because beta is here, right? If you were here, you would determine your alpha, your silver composition. Here we want to determine the copper composition. So, yeah. Does it make sense to you guys? Like, it makes sense to me now. When I was in my first semester, I mean, when I was in my first year, it didn't make any sense. I don't remember.
Yeah, it kind of doesn't make any sense, to be honest.
Yeah, yeah, sure, makes sense. Oh, okay. How would I reiterate that? Okay, you're in slushy region. You're in the semi-solid region. Yeah. If you keep increasing temperature, you will go to liquid. Let's say at some point in time, like crucible and like inside your crucible, you start melting your stuff. And then at some point in time, you stop, you make a picture. This is like a magic picture that you can observe, like, which will give you the amount of liquid and amount of like an amount of solid in your metal, right? So you were like increasing temperature, you stopped, you made a picture, and you kept increasing, and you don't care anymore. Okay. So in this picture, you can analyze. Okay, you grab your phase diagram. Okay, and you know that at the temperature of 820 degrees, let's say, right? You made this picture. So you start drawing the horizontal line. Okay, it's called a tie line. You need to draw in order to basically apply the ratios of your liquid to solid, solid to liquid, pretty much. Since you're given the composition, this is 90%. Because you know what composition you put into your crucible, right? Otherwise, like, you don't know what you're doing, right? You put 90% of silver, 10% of copper, right? So you took that picture, you understand the time, understand the temperature at which the picture was taken, right? And now you're like wondering a question, why, not why, like what I'm looking for. So let's say I want to find my beta phase, right? I want to find the amount of copper that I have at that instant that we took a picture, okay, that instant. I want to find the amount of copper, right? Basically, a weight% of copper is what I'm looking for. Okay. So is C0 85? No, C0 is not 85. I'm going to be talking about that. Your C0 is going to be 90%. So 0, think about it as initial condition of your composition. So your initial condition is actually the metal you put into your crucible, which is 90% of copper, of silver, sorry. That's 90%. Okay. So C0 is 90% here. Okay. Your CL is going to be equal to 85% because it's basically a liquid point. So this liquidus line okay, you have 85% of your silver. That's what it says. Because as I was describing before, on your liquid line, you're still staying in your slushy semi-solid region. You will not be perfectly liquid here. As you pass that point, you will be perfectly liquid. But here you're still having some solid left. Okay. So basically, it's like your initial condition. So you took that picture and you know that it's 85 weight% of silver at this point. 85 weight%. So you get this, draw your vertical line on here. This is 85 weight%. Okay. So, and then you're trying to find basically the composition of the beta phase. Okay. So composition is going to be our W. Okay. From the timeline, you can visually observe that not the composition, that the C value of your beta will be around 95 degrees. 95%, my bad, 95%. Okay. And we will call it a C beta. Okay. So this is like a composition percentage. Okay. And we're looking for the weight percent. Okay. So this is a weight percent, what we're looking for. And this is like a concentration. C, it's like a concentration. So we have a concentration of 90% of silver, 10% of copper. Okay. And you're trying to find the weight percent, right, of your beta phase. So the weight percent here, you don't know what that is. Okay. But that's what you're trying to do. And the equation in order to find your weight percent based on your composition is somewhere here above. Here we go. So it's C0, so your initial concentration of your metal minus the concentration of your liquid region, of your liquid on the liquidus line, divided by C alpha, which is C beta in our case, okay, which is the concentration of your copper on the solidus line, minus the concentration of your liquid. Okay, so this will give you the weight percent. Okay, so if I rewrite this in terms of the equation, so your weight percent of beta is C0 minus CL divided by C beta minus CL. If you were to take a look, it's actually basically the distance between here and here divided by the total distance here. Okay, but that's pretty much a ratio using the tie rule. Again, might be confusing. Let me talk about it again. So you are given the initial composition of your metal, right, which is 90% and 10% of copper, right? You basically find this point here. Then you take a snapshot when you increase the temperature. You take a look at the time, which is 820 degrees, right? And then you're trying to find the weight percent of your beta phase, okay? So you're given that you have on the liquidus line, okay, the amount of liquid that you have is 85 weight% of silver. Okay, so you actually drop down, the concentration of that is going to be 85%. Okay, of silver, so it's right here. Then you draw a tie line, a horizontal line parallel to compositional line here. And this will intersect the solidus line. So you drop down your vertical and you find 95% of your silver. Okay, inside here on this solidus line. Okay, so you want to find the amount of beta phase, amount of copper inside your alloy at this specific location at that snapshot. So this is right here. This is the point where it is right now, right? So you basically start taking the ratio of the distances between your initial concentration, your left boundary and right boundary, pretty much. So your C0 is going to be 90 minus liquid, which is 85, divided by 95 minus 85. So the end is going to be 5/10, so it's 50%. Even visually, you can observe it's like almost in the middle between 2 points here, between liquidus and solidus. It's like 50%. It's like in the middle. Okay. Sorry, question? No question. Okay. Any questions about that? So like obviously if weight percent of beta phase is 50%, then the amount of liquid is going to be 50% as well. And the reason you have beta and liquid is because this region is semi-solid and you do have beta and liquid only here. You see, so we were kind of given that we're in the beta plus liquid region. So in here you will have beta and liquid. And we found that at this snapshot of time, at this temperature, the weight percent of beta is 50%, which means the amount of liquid is the same. So basically it's exactly the same amount of liquid and solid. So WB is the composition and CB is the concentration. Okay, it's very confusing because it does say weight percent here. Okay, I know, but I'm kind of like saying that this is concentration so that you can guys kind of visualize and understand what that is. Okay, see, like it's kind of a concentration. Think about like that. Okay, and then when you're trying to find the weight percent, you take the ratios of concentrations. Okay, so think of it like that. Might be incorrect. I do understand it, but think of it like that. Okay, I know it's really hard. I know it's hard, so I'm trying to make some things, for you guys so that you can understand what's going on, right? Did you get it? Like, because like, imagine if your original concentration of your metal was like something like here, it was like 87, right? So you would be observing here now, right? Let's say at this point. So as you can see, this distance is larger than this distance, right? So you can expect to have more liquid and less solid. Okay, sorry, my bad. Less liquid and more solid here. Okay, it's inversely proportional basically. But since we were like in the middle here, we can expect 50% of that and 50% of that. Okay, let's do a quick example here. We have 30% of silver and 70% of copper, right? So we were increasing the temperature and we want to observe what happens exactly at 900 degrees Celsius. Right here, right? So you have this and you have this. You draw a line, right? So from here, you can observe that this is going to be 18%. This is going to be like 45, let's say, percent. Okay. So now, how do we know where the point goes within the area? Which point? Are you talking about the point, this point within the area? I think so. Yeah. Yeah. So, how do you know where this goes? So in here, you were given the 85 weight percent, right? So if you were to, basically the way I approach this problem is I found 85, after finding the concentration here, 90%, I found 85%, which is here, right? And then if you draw a horizontal line, you will intersect this vertical line here, right? So it means this is going to be the point of your interest. This is where you are, basically. Or otherwise, instead of giving the, the liquidus weight percent, you might be given like a temperature. Isn't it meant to be 8%, not 18? Oh yeah, you're right. Sorry, my bad. Should be 8%. My bad. Thank you, makes sense. Yeah. So let's do a quick example here. Okay. It's easy as long as you get it, guys. I know it's conceptually difficult, but so let's say here I was given in my question to find the amount of, let's say I want to find the amount of my alpha phase in the semi-solid region. So why it's not beta? Because we have only alpha plus L. Okay. Why is that so? It's just because the phase diagram says you so. Okay, it's just like do the way the diagram shows you. Okay, so this composition of alpha solid and composition of liquid is what you're looking for, and they give you at okay. Here's like my question that I just did. Okay, so given, let's say given 30% silver at 900 Celsius, basically you want, oh shit, not percent Celsius, you want to find the weight percent of your alpha, of your solid region, of your solid amount of your solid, pretty much. So what do, you find your 30% here, then you find your temperature. You draw two vertical lines, here, you find the intersection between both. Then you basically draw a horizontal line, time line, which intersects this semi-solid region here at solidus and at liquidus lines. Okay, so now you're interested, what is the composition of, what is the amount of solid that I have here, right? You don't know. So you assume everything is linear, so you do ratios, right? So basically what happens is your omega alpha is equal to C0 minus CL divided by C alpha minus CL. So what is our C0? 30%. What is our C alpha? Is 8%, right? This is basically the amount of solid that we have in the solidus region, right? And C of liquid, right? Because this is C of alpha concentration line, it's a solidus line. C of L is a liquidus concentration, so it's a liquidus, so it's CL pretty much. CL, 45%. So easy peasy. You plug in 30 minus 45 divided by 80, no, not 80. What is that? 8 minus 45. Okay, so you get like 15 divided by 37. So let's find what that percentage is. 15 divided by 37 is going to give us 40.5%. 5%. So obviously the amount of liquid that you have is going to be 50, sorry, not 50, yeah, 59.46%. Should make sense to you guys, right? You can also do the same. Well, doesn't, yeah, it kind of makes sense to do it here, I guess. No, well, yeah. You can also do it here. Same approach, okay? You can do it here, you can do it here, you can do it anywhere. That's going to be like probably the midterm question, just a tie line. So hopefully it makes sense, okay? So given you have 30% of copper, silver, 70% of copper, find me the amount of solid in this semi-solid region at 900 Celsius. So you draw your 900 horizontal, you draw your 30% vertical, you find their intersection point, you find the intersection points, and you draw a horizontal line between the solidus and liquidus. You take down vertically the amount of percent here, and then you use the equation and you find the percentage. That's it. Wait, doing that on my calculator, I got 41. Shit, really? 15 divided by 37. Well, that, I mean, yeah, it's close enough to 41. So should it be 45 minus 30? 45 minus 30. No, because you will get a negative answer at the end. You cannot do that. So the person is asking me, shouldn't it be 45 minus 30? My answer is no, because you just follow an equation. 30 minus 45, right? This will be negative, divided by C alpha minus CL, which will also be negative. You want to cancel out 45. Oh, well, you mean that? Oh, yeah, sure, you can do that. You can swap. Yeah, it doesn't matter. You can have CL minus C0 divided by CL minus C alpha. It doesn't matter. Yeah, that's what you're asking. Yeah. Why do we look for WL? We're looking for WL. I mean, if you're asked to find WL, then you can find WL. It's the basic amount of liquid that you have at this point. Okay, when I do that, I get 41%. What? 45 minus, I mean, it's the same number. It's just 15 divided by 37, 40.54, which is close to 41%. Okay, so why do we look for WL? It's because if you're being asked to find WL, you can find it. Since we know the composition, the amount of solid that we have, why not just define the amount of liquid, right? So it's just 100% minus that. Pretty much, Okay, anyone has any questions? Because we have to wrap it up. Okay. Does it make sense here? Again, try to understand it also at home. Watch like my recording again at this specific point. Okay. So thumbs up, we're good to go, because I'm going to do last question and we're going to wrap it up.
Is this
Okay,
max
perfect.
difficulty question we're gonna get in a phase diagram like this type, or we're getting like
Yeah.
one of those lead magnesium diagrams?
That's just one of the questions again. Again, it's not difficult, honestly. When you start working on this on your own, you're gonna see it's so simple. You just like do that, you intersect, you find that point. on the diagram you find composition, use one equation, literally one equation, and you're done.
Yeah,
Yes,
it makes
if
more
you
sense
practice
now.
that, yeah,
But I'm just
if you
worried
practice
we're
that,
getting one of those lead magnesium diagrams.
are you talking about that? Oh Jesus. Okay, here. Okay, you better not be given that. Okay, well, how would I do that here? Well, okay, look, it's still not complicated. It's the same approach, okay? If you are given 35% of, okay, look, it's not difficult at all. You have literally same strategies. 35% of what, 10 here, or lead, sorry. You draw your line. Let's say you're given to find it 50% decomposition of the amount of solid and liquid. So you basically, again, you touch these points, you find that this is 20, this is like 55, and then you're doing the same shit. You like 35 minus 55, you divide by 20 minus 55, right? So you're gonna get like 20 divided by 35. Just gonna give you 57%. Like, look, I just did it like in a minute. That's it. Like the reason it took so long is because like I was explaining to you guys all this stuff. But as long as you understand the concept, like it's so simple. So the amount of alpha base that you have is like, yeah, and the closer it is to this solidus line, the more you will have. So look, even visually, you can observe that this one is like closer to the solid line than the liquid line. That distance is larger than this, so you should observe more solid than liquid. So liquid is going to be like 43%. Okay, so the weight percent of solid we found first will always help us to find the weight percent of liquid from the subtracting 100. Yes. Yes, that is correct. Correct. Yeah. This is like the most amount of complexity you can get, guys, on the midterm or final exam. Yeah. You can do it in this region, in this region, in this region. Super, super, super simple rule, guys. So basically memorizing the whole theory will make everything make sense. Kind of basically memorizing the whole theory. Yeah, it will definitely make sense. But also the way I described it, because like I was memorizing all the theory in my year, and it didn't make any sense to me until I actually worked on stuff in material science in my lab. But now since I have this experience, I can like pass over some information to you, and the way I understand it now should make sense to you now. Okay, so yeah, back in my day, nobody could explain to me like what the heck is that. So I had to like suffer seriously here. Hopefully that makes sense to you now, guys. Yeah. So okay, that's 3 nights without sleeping. Pretty much, man. Yeah, like you have to read a textbook. I read the textbook twice. I remember all the chapters before the midterm and before the final exam. Yeah, that helped definitely. Also, make sure you're taking notes when you read the textbook. But yeah, my document should be like also good. So before you go, before you go to your midterm, take a look at my document just to refresh your memory. But that's a lot of stuff. It's heavy course, yeah. Okay, let's do one last question, guys. One last question. So that's going to involve the Gibbs phase rule. Okay, that's typical question in the midterm. Yeah. So okay, what is that? Oh yeah, that's the question. So in figure 9.38 is shown the pressure, temperature, phase diagram for water. Okay, H2O. Apply the Gibbs phase rule at the points A, B, and C. That is to specify the number of degrees of freedom. Sorry, at each point, that is the number of externally controllable variables that need to be specified to completely define the system. Okay, a lot of words in this question. That is quite simple. What you have to do is apply only one possible equation for the Gibbs free rule, which is P plus F is equal C2 plus N. So, okay, I do it once, and you will guys like pretty much just like memorize it forever, honestly, for your midterm. So what is P? Okay, P. P is, okay, let's go up. P is the number of phases. So number of phases, okay, it basically means the number of physical states that you have at a specific point, right? So number of physical states. Okay, letter F, variable F denotes for degrees of freedom. So basically, how many parameters do you need to control your experiment? Like pressure, temperature, what else we have? Like some other stuff, like pressure, temperature, you know. So C denotes for C denotes for number of components. Okay, so in eutectic structure, so here obviously you will have like copper and silver, right? So that will give you like 2 components. So your C will be equal to 2, right? In this course, it doesn't go beyond 2, so it's either 1 or 2. So in this case, it's 1, right? So number of elements. So it's water, just 1 element, and whatever. So N is the number of non-compositional variables. Right, so basically N, sorry, let me scroll up, take a look what it says there. So basically number N variable is the number of so basically it's the amount of variables that exist in your current system. So it's a pressure and temperature. Okay. What are we looking for here in this case? The number of external. Okay, so F, okay, F is the number of external variables, which defines the degrees of freedom of our system. So let's say this is like external means that something they do not control. Okay, so if you in your system N defines the number of parameters that you can control, F denotes for something that is external and you do not control that. So let's say N, in this system, we control pressure and temperature. Let's say outside, there is another parameter like time, let's say time, and we don't care about it, right? So that's like a degree of freedom that exists in our system, right? So, or like altitude, right? So with the increase of altitude, you will change your density and temperature, right? So that's like a external variable. So you would like it was the increase of altitude, this thing will fully change. That's like another degree of freedom. You can also have degree of freedom like altitude and again time, right? Something like that, if you know what I mean. So N is going to be the again parameters that you control in your system. You know that you can crank pressure up, crank temperature, and you will get something, right? So, okay, so let's observe. We have 3 different points. We have A, B, and C. Let's find, what are we looking for? Blah, 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 blah. Degrees of freedom. Okay, so external degrees of freedom. So basically F, we're looking for F. And we know that we have P plus F plus C plus N. So at point A, we have P as the number of physical states, right? So at this point, I think it's called the invariant point. That is really a weird point when it exists in ice, liquid, and gas, right? So we have like 3 states pretty much. Am I right? Right? P, sorry, let me refer quickly to the solution manual. Yes, correct, perfect. Okay, P is equal to 3, that is correct, because at point A, it is an invariant point. We exist at the same time as liquid, gas, and liquid, gas, and solid. So P is equal to 3. Number of elements, only 1. And N is equal to 2. So simply 3 plus F is equal to 1 plus 2. So F is equal to 0. So no degrees of freedom. In this system, there are no degrees of freedom. So it's a stable system. Okay, we cannot change anything except pressure and temperature. Let's take a look at point C now. On this line, we know that the molecule of water will be at the same time solid and liquid. Will be solid and liquid. So our P is going to be equal to 2. Our F is going to be equal to, we're looking for F, sorry. Our C is going to be equal to 1. C will never change in this question. Sorry, what was n equal number 2? My audio got out. Yes, n is equal to 2 because you have pressure and temperature. Only two variables that you can control in your system. Just remember, n is the number of variables you control in your system. P is the number of physical states. C is the number of elements. And F is the amount of external degrees of freedom that you have in your system. That's it. Oh, right. Okay. C is equal to 1, N equal to 2. That will not also change. So F is going to be equal to C plus N minus P. So 1 plus 2 minus 2 is equal to 1. Okay, perfect. So you see, like, at this point, you will have 1 degree of freedom. Can be equal to 1. Yes, it will be equal to 1, and we're going to see where it's going to equal to 1. Actually, it's going to be equal to 1 at point B. So we're going to work on this point B now. So at this point, we only have one state, which is vapor. So it's like gas, right? So only one state. Physical state is 1. So here we had only 2 physical states because it's lined on this line. This is a varying point. So 3 states at the same time. So C will not change and N will not change. So our degrees of freedom will increase to 2. You see? So invariant point is quite stable. You cannot change anything. It just exists, which makes sense. It's a really rare point. So experimentally, it's really hard to like get into invariant point. If you're interested, take a look at some videos about invariant point. It's really like crazy. Like the water is like at the same time liquid, gas, and solid. Yeah. So yeah, at this vapor region here, you will always have 2 degrees of freedom. Here you will always have 1 degree of freedom. On the lines, you always have 1, and on the intersection of lines, you always have 0 degrees of freedom. And that's pretty much it, guys, for today.
So I got a question.
Yeah.
What do these number of freedoms or degrees of freedom actually mean? Like, is it like a thing behind it? Like the bigger value of it, does it change anything?
Yes, like altitude, like density.
Okay.
Right? Like time, which is like, I don't know how the time would impact that, but like density will, right? If you increase your density, the pressure temperature will change. Like as they increase of altitude, your pressure decreases, right? So obviously, like the invariant point, what it means is that no matter where you are, you will have that under this pressure and under this temperature. Okay, but like, because like there are no degrees of freedom to change, like, so whatever. But here, there is a degree of freedom. So if you start changing an altitude, let's say, like rip, this is no longer going to be like that exact the same point. It's going to move. Yeah, if it's going to be at an altitude of like 10,000 kilometers, then your gas is going to turn out into solid, right? So it's going to move down to here, pretty much. Yeah, so it's like a degree of freedom, like altitude, like density or something, like temperature, right? Oh, sorry, not temperature, like, yeah, another variable from here. That's what it means, yeah. All right, any other questions? It was a really long study session, guys. Jeez. So, okay, I'm gonna be posting soon. Again, on my website. If somebody doesn't know my website, here's again my website. I'm gonna post all my stuff there. And yeah, so you'll find the YouTube video there. Answers to the study hall. And yeah, let me know if you have any questions. What was F at A? 0. Invariant point. So no degrees of freedom. Yeah, there are like no external parameters that you can change. Yeah. Okay, cool. All right, guys. I guess that is it for the tutorial. Thank you so much for being here. Please ask me any questions if you have. Thank you so much for the study. I'll appreciate it. Have a good weekend. You too as well. Thank you. Of course. Thank you. Thank you for coming. Thank you, guys.
Thank you.
Have a good one. Thank you so much. Appreciate that. Thank you. I'm gonna stop the recording now.